Hello, everyone. Can the audience hear me clearly?
Yes.
Okay.
Can you hear me?
Yes. Yeah. Thank you.
Okay.
Yeah. Okay. I'm really glad to have a chance to hold such AI seminar. We actually have, I think, more than 100 registration, but I believe the seminar is, I know it's too long, but you're welcome to leave and go just to go to your favorite or your interested session. But let me just quickly introduce today's schedule. So we have 3 different sessions for the talks only, but also we have a special session for a panel discussion in which we would like to touch base on the ChatGPT topic. So the first session would be recent advances in medical science. Then session 2 would be about natural language processing, and then the last session would be about recent advances in machine learning. So very quickly, let me just introduce you to the first session, the recent advances in medical science. So in this session, we have 2 speakers. So the first speaker is Tianxiao Li from Yale University. And then the second speaker is Dr. Liu Yaoxu. He is from IBM Research. So Tianxiao, maybe you can just go ahead and share your screen for the talk. Thank you.
Okay, sure. Let me have a try sharing the screen. So can you see the slides?
Yes.
All right, great. So shall I just get started?
Yeah, maybe you can quickly introduce yourself and then
Sure.
you can start your introduction. And I think the audience, maybe you can hold your question and then we'll have a question answering for after the talk. Thank you. Yeah, go ahead.
Okay. Okay, so thanks, Irene, for the introduction. My name is Tianxiao Li. I'm a graduate student from Yale University, and it's my great pleasure to talk about my work on data-driven T-cell receptor design. So first, I would like to provide a brief biomedical background. So one of the hallmarks of cancer is the ability to evade the human innate immune system. That is to say, the malignant tumor cells cannot be properly detected or destroyed by the patient's own immune system. So this gives rise to the method of adoptive immunotherapy, where we provide a patient with either naturally occurring or engineered immune cells that the patient themselves cannot produce to enhance their immune system. And in this work, we are focusing on T cell, which is one type of immune cells. And so T cells have a surface protein called T cell receptor, and that are mainly responsible for recognizing specific antigens and trigger downstream immune response. And the human body is able to produce a wide variety of TCR pools, and each has their own binding specificity. That is to say, a certain type of T cell receptor will only recognize a certain type of peptide antigens. And so because of this, it is possible to engineer the TCRs so that they gain the binding affinity towards a new or novel peptide antigens that could be used to enhance the patient's immune system. So here's a sample of the interaction complex between a TCR and the peptide and the antigen. And you can see the one of the regions called the CBR3 beta loop is generally believed to be mainly responsible for recognizing the binding specificity. So here in the later parts, when I'm talking about like designing a TCR, I'm almost talking about designing the CBR3 beta region unless specified. So there are some existing methods already, existing computational methods for TCR design, which mainly involves physical modeling and homology modeling. So the pipeline is usually manually introducing mutations into the TCR sequence, and then use physical modeling methods to estimate, to evaluate the binding energy, and use that to evaluate how good that interaction is. So this process is usually quite time-consuming and requires significant domain knowledge, and cannot be done in high throughput. So the motivation of this work is to instead design a data-driven approach that makes use of our current knowledge about known TCR peptide interactions to direct TCR design. So specifically, we curate the experimentally validated TCR peptide interaction pairs from several databases, and we use those as our positive data. And because we believe that TCRs are highly specific, that is to say, if we know that a TCR already interacts with a certain peptide antigen, it is not likely to interact with the others. So we randomly shuffle the positive data to gain the negative pairs. And we represent the data pairs, by the primary sequences of the CBR3 beta region of the TCR and the peptide, which is a sequence comprised of a vocabulary of 20 amino acids. So the basic assumption of our method is that we believe there are certain sequential patterns in the TCR sequence that are responsible for peptide binding. That is to say, we call this the functional patterns. So that is to say, there are like a small group or specific defined positions in the TCR sequence that indicates which kind of peptides they interact with. And we want to separate this kind of those patterns with what we call the structural patterns. Those are the rest of the sequential patterns that do not directly relate to peptide binding, but more responsible for defining a sequence backbone or maintaining the overall protein structure. And so we can use two types of embedding vectors to capture those two types of patterns. And in this way, we kind of formulate this problem as a style transfer problem similar to those in natural language processing or computer vision, where you want to maintain the quote unquote content of a sentence or a picture while changing the style of it. So in this case, we would like to maintain the overall structural backbone so that it is still a valid TCR and modify some very specific pivotal locations that changes their functions. In this case, the function is their binding specificity. And we also want those two embeddings to be disentangled so that they do not share any mutual information. So in this case, we'll be able to safely edit the functional patterns without like disrupting the structure of the whole protein. And we will see later why this is actually very important. So now if we can achieve the disentanglement between those two types of patterns, we will be able to modify the function of a TCR by modifying only the functional embedding. So for this purpose, we designed an autoencoder with a disentangled latent space to achieve this goal. So we have two separate encoders that encode the input TCR sequence into the two embedding vectors, so the functional vector and the structural vector. So we, in order to achieve the disentanglement, we we add two additional losses, auxiliary losses, on top of the normal reconstruction loss of the autoencoder. So first of all, we want the functional embedding to encode the functional information. So we build an auxiliary classifier on top of it and use it to predict its peptide binding specificity. And secondly, we want to achieve disentanglement. So we also use a Wasserstein loss, enforce a Wasserstein loss on the distribution of the whole latent space so that it approximates a Gaussian distribution, a normal distribution with unit diagonal variance, so that the dimensions are independent with each other and they naturally have no mutual information. So we use this framework to separate the two important patterns that constructs a TCR sequence. And so we first look at the effectiveness of the disentanglement. Here we show the t-SNE plots of the functional and structural embeddings of certain subsets that corresponds to a specific antigen. So in this case, you can see that in the functional embedding, we'll be able to separate the positives from the negative, while they're mostly indistinguishable in the structural embedding. And also the correlation between the dimensions are almost minimal. So this indicates like the minimal mutual information constraint is successfully enforced onto the latent space. And we also combine all the positive sets for different peptides and plot them together. And you can see there is a rough separation between the groups of TCRs that recognize the same peptide, while in the structural embedding, the separation is much poorer. So after the model is trained, we then can use it to do the TCR sequence modification or the design part, as I have just described. So for this, we feed a template TCR sequence, usually a TCR that does not bind to the desired peptide or does not have the desired function, and we obtain its embedding vectors. So for the generation, we keep its structural embedding while modified its functional embedding from a negative one to a positive one. And then we combine those two embeddings and feed it to the decoder so that it will produce a sequence that is generally similar to the original in its like generic backbone, but there are some parts modified so that it gains the new function. So to evaluate how good our generation is, we use two sets of criteria. The first criteria is whether the generated TCR is still a TCR. So for this purpose, we train another autoencoder on a very large external data set of TCRs. And then for our generated sequence, we feed it to the autoencoder and evaluate how well it can be reconstructed and whether the embedding space whether their embedding is close enough to those of the known TCRs. And we show that here that score actually works quite well on the known TCR sequences, and as they are scored much higher than randomly sampled protein sequences. And the other criteria, of course, is whether it really gains the function we want. So we use a published classifier called Ergo that takes as input the sequence of the TCR and the peptide and produces a binding score. And we use that to evaluate whether the generated TCR gains the desired function. So we also compare our methods with several search-based baselines. So the basic idea of those methods are pretty similar. That is to say, given a template, we iteratively, for every round, we randomly introduce mutations, and then we evaluate their functional scores. And then we select those sequences, those generated sequences that have the highest score, and then use that for the next round of mutagenesis. And we do this like several steps until we have a large enough pool of sequences that we want. We also and this includes like greedy search or genetic algorithms. And also here we have a control here called random mutation that is just introducing random mutations without any selection. And we also tested other kinds of de novo sequence generation approaches, such as multicolor tree search. So here we also test several different ways of obtaining the positive embedding vector. So best means we are using the embedding of the sample with the highest binding score. And average means we get all the positives and we get the embedding of all the known positives and we take their average as the new embedding vector, functional embedding vector. And random means just randomly selecting one positive sample and use this functional embedding vector. And what we can show here is that we report the proportion of both valid and positive sequences in the generated sequence set. And here we show that our method can outperform the baselines significantly. So one thing that is worth mentioning is that for those search-based method, it is possible to achieve really high binding scores, but most of them are no longer valid. So that is to say that because there is no control on the sequential backbone, and it is possible that those methods will generate sequences, artifact sequences that are totally out of the distribution, but the classifier somehow predicts a higher score for them, but that score is not useful because the sample is not from the same distribution of other TCRs. So this also demonstrates the importance of having the control on the structural embedding, which defines the general backbone of the sequence, so that it does, but in the generation process does not generate like sequences that totally does not make any sense. And the other major advantage of our method is that it runs much faster because it only requires one pass for the generation after training, and you do not need to do several rounds of introducing random mutations and calling the evaluation model. So in fact, our model is trained unaware of either objective we want to optimize here, but it's still able to achieve like pretty good in both. And we also further investigate whether whether our trained model can capture some underlying mechanics of protein-protein interactions. But for example, the stability of the interaction complex is mediated by the interactions between their specific amino acids. So here we use a very coarse-grained energy estimator called the Miyazawa-Jerningen energy matrix to like roughly estimate the binding energy between the TCR and the peptide. And here we show that for the generated positive set, they are able to achieve much lower energy score than their negative templates. And that level is almost similar to known positives. And for one specific case, we can see that the introduction, the modification of the TCR here actually introduces the possibility of forming much lower energy interactions with the residues in the peptides, which means that the model might learn strategies, modification strategies that go towards like lower binding energy. But this is very coarse-grained. It needs more in-depth analysis. So as a conclusion, we use our method. We design a model that can efficiently generate high quality and large quantity of candidate TCRs with the desired function. And also we can use it, we can extend it to any other desired properties in protein design, as long as you have a high quality label for it. And there are also some remaining challenges and limitations of the methods. First of all is that even though we are mainly focusing on CBR3 beta, and the CBR3 beta is generally believed to be the one that is most responsible, there are also studies that show that CBR3 beta itself is not enough. So because if you look at a complex, there are several other like loops and the molecules involved in this process. So we might also take into account like other players in the interaction. And also 3D structure is very important. Even though we believe that the sequence could encode all the information we want, either the model or the data set is not large enough for us to capture all of the patterns. So we probably need to explicitly provide the structural information to the model so that it improves the modeling quality. But then the problem is the structural data is really scarce for TCR peptide interactions. And one other thing I would like to bring up is that for sequence-based models in general, they like the studies in TCR have like really poor generalizability. This is observed in many studies, mostly for classification of TCR peptide interaction. But because our model also relies on a classifier, it could also happen in our model. That is to say, because the variations in the peptide on the peptide side is really low, and only a very small number of peptides has large enough pairs to be sufficient for the modeling. So as a result, the model is more likely to like memorize certain peptides and try to push the TCRs like that correspond to each peptide as distant from each other as possible, but they're not really learning the interaction between the TCR sequence and the peptide sequence. So as a result, the model can achieve like really high performance in the validation set of the same peptides that it has seen during the training, but when it comes to a non-same peptide, the performance drops significantly. And the other thing I would like to bring up is that the interaction not only requires like the right type of amino acid, it also requires like a proper spatial arrangement where the amino acids are spatially permitted to actually make the interaction happen. So in this case, it is also very important to take into account the 3D structure information. So here we did a small pilot study just for the classification. So because the structure data is scarce, we use homology modeling to obtain the structure for those that are not, for the pairs that are not available. And then we represent the structure into a 3D graph and use a 3D graph convolution neural network to predict their binding specificity. And here we show that on the same peptide in the training set, using 3D structure data can significantly improve the generation performance. But because this analysis is only carried on a very small set of data, it should be taken with a grain of salt. But nevertheless, it still demonstrates the importance of incorporating 3D structure information into the analysis, into both the prediction and also the generative modeling. So that's all for my presentation. I would like to thank my academic supervisor, Mark Gerstein at Yale University, and also our collaborator, Martin Min from NEC Labs America. Okay, thank you very much for listening, and questions are welcome.
Yeah, thank you so much, Tianxiao. This is a really amazing talk. I think we received a question in the chat. So this is from Renhe Jiang. He asked, apart from protein, are there any other sequence-based problems in the field of AI for science?
If you say for science, probably that you are excluding like computer science, such as natural language processing, right? That is a natural sequence-based problem. But I think for proteins, they are, at least in biology, I think one of them would be like DNA and RNA, right? But our understanding of them are much poorer. And so, but nevertheless, I think they should be, those are also sequence-based method. And a natural extension of this would be graph-based problems, such as like both protein structure and small chemical molecules.
Yeah, I see. Yeah, thank you. Let's see. So back to the audience. You're free to unmute yourself if you have any questions. Okay, so we have another pop-up question. Yeah, you can read it. Yeah.
Yes, and immunotherapy for cancer is very expensive. So is it possible to use your approach to reduce the cost? Yeah, I think that is a really good question. One of the things I think that is my understanding for most of the computational methods for either drug design or this kind of candidate generation, that is to like, because the search space is too large, right? Because the protein, whether it be protein or chemical molecules, the possible conformations, the possible candidates we have is the search space is too large, and it's I think it is impossible to like massively select like the really good one from doing a lot of experiments, because that is really expensive. But I think most of the computational methods go down to generating a much smaller set of candidates than for the experimentalists to further investigate, because experiments are expensive and takes time. So I think our method, and this method I would say is a very pilot one. I think for a more serious or like more real application, we probably also need to take into account the 3D structure. And we also need to accumulate a much larger data, as I have mentioned, because the low variance in the current data set, the generalizability is poor. So it is still not able to really target novel antigens. So I think the eventual goal of this kind of study is to, like, say, for example, we have a personalized immunotherapy problem. We have say, for example, the peptide fragments of a specific type of tumor cell from a patient, and we have the pool of TCRs that are generated from the patients that the patient can produce. We can probably use like computational based methods to design to prioritize maybe a set of 1,000 candidate TCRs, and then we can do like maybe experimental validation on their effectiveness. So that is, I think, one of the ways that the computational methods can be used to reduce the cost. Maybe not the cost of immunotherapy itself, but the cost used to develop it.
I see. Yeah, thank you, Tianxiao. Let's allow for only one last question from the audience, if there are any. Okay, yeah, I think that's all from Tianxiao for his talk. Yeah, thank you so much for giving this talk. Okay, so let's move on to Dr. Lu Yaoshi. He is a research scientist from IBM Research. So Lu Yao, feel free to share your screen and start. Thank you.
Yeah, I'm trying to share the screen, but it says a host disabled participate.
Sorry. Now you can do it. Thank you.
Okay, give me a second.
Yeah, you can see it.
Okay.
Yep.
Okay. Thanks, Dr. Lee, for Thanks, Dr. Lee, for hosting and inviting me to this AI seminar. and it's a great honor for me to present my work here. So my name is Lu Yaoshi, and I'm a staff research scientist at IBM Research in the US. Today, I'm going to talk about the uses of synthetic data in machine learning for healthcare. Give me a second. Okay, synthetic data has been widely used in machine learning nowadays, particularly for machine learning for healthcare. There are many benefits of using synthetic data. The first one is cost-effective. So generating synthetic data is often less expensive than collecting and annotating real-world data. And also, synthetic data can be generated in large quantities, which can be useful when real-world data is limited or difficult to obtain. And they also allow us to explore rare data, because sometimes the real data are rare and can lead to biased training. But when synthetic data, we can generate a lot of them to avoid that problem. And they also have increased privacy. In many cases, healthcare data is highly sensitive and may contain personal information that needs to be protected. By using synthetic data, researchers and healthcare professionals can avoid sharing real data and reduce the risk of privacy violation. And last but not least, synthetic data can lead to improved patient outcome. So in this talk, I'm going to illustrate 2 examples of using synthetic data from my personal research. So the first one is with the application of medical imaging on the computer vision side. And the second one is medical information retrieval on the NLP side. So the first one is generating attenuation map for SPECT-only systems using generative adversarial network. This is the work from when I was a PhD student at Yale University. First, let's take a look at what is SPECT. So SPECT is a single photon emission computed tomography. It's a non-invasive functional imaging modality. The way it works is that the doctors inject radio-labeled tracers into the patient body, and those tracers will decay and emit gamma photons. And there's a detector around the patient body that rotates around the patient body to collect those photons. And with image reconstruction, we can measure the distribution of targeted tracers in the body and lead to diagnosis. So there are many clinical applications for SPECT, including myocardial perfusion imaging, brain imaging, bone imaging, and tumor imaging. So we all know that human body is mainly water, right? And the gamma photons will attenuate when they travel within the human body. And therefore, accurate attenuation correction is essential for SPECT imaging. Without attenuation correction, attenuation artifacts can be seen in the SPECT images. For example, here we show a uniform phantom. And if we do not use attenuation correction, the reconstructed images will have these ring artifacts. If we turn on the attenuation correction, we can see the reconstructed images is uniform. Many recent hybrid SPECT systems are equipped with a CT scanner that can be used to measure photon attenuation. So here we show a hybrid CT SPECT scanner. There is this SPECT scanner in front and CT scanner in the back. So after patient obtain a SPECT scan, it will immediately receive a CT scan to acquire the CT images. And later, image registration is performed between CT and the SPECT images. And the CT images can be converted to attenuation coefficient to perform attenuation correction for the SPECT images. However, there are many limitations for the CT-based attenuation estimation. The first one is very expensive, and it requires larger imaging rooms, additional light shielding, and more complicated acquisition protocols. Moreover, it delivers more radiation dose to patient, which is not healthy and can potentially lead to cancer. Also, there are sometimes mismatches between the CT and the SPECT images, which will result in image artifacts. So here we show an example of the CT images and the SPECT images. So when they are perfectly registered, the SPECT images are like great. But when we do not have the CT images for attenuation correction, there are artifacts here. And when there is a poor registration between the SPECT and CT images, there are also artifacts. Unfortunately, 80% of the SPECT markers are standalone SPECT systems, which means we do not have the CTs to perform attenuation correction. For those machines, they are susceptible to attenuation artifacts. So estimating attenuation map using only the SPECT emission data will have a strong clinical impact. We found that both photon peak photons and scatter photons contain information that could help estimate the attenuation distribution. So from the image examples at the bottom, it can be seen that both the primary window images, mainly contain information about the heart and other inner organs, whereas the scatter window gave more information about the body boundaries. So on the top right, we show the primary and the scatter window from the energy spectrum. So the existing segmentation-based and model-based approaches are either time-consuming or not accurate. So we propose to estimate attenuation map from primary window and scatter window photons using deep learning. So in our study, we train a generative adversarial network, commonly known as GAN, to synthesize attenuation map. Using the real CT attenuation image patch as the ground truth label. So the SPECT image patches from both the primary and the scatter SPECT images can be fed into the generator network to produce attenuation map image patch. We use a UNet as our generator. The goal of the generator is to generate realistic synthetic images that can confuse the discriminator. On the other hand, the discriminator trying to tell if an attenuation map is a fake or real. So the discriminator competes with the generator and improves the generator. So in the end, we can use the trained generator to produce realistic attenuation map images. So to evaluate our proposed method, we acquired 65 patient studies from Yale New Haven Hospital. We used 40 of them for training the network and 25 of them for testing. So all of the studies are acquired with the corresponding attenuation CT scans. So at the bottom, we show in training and testing data, the patients have similar distribution regarding gender, age, height, weight, and BMI. So here we show some examples. This is the primary window images, and this is the scatter window images. And so it can be seen that our synthetic data is very consistent with the true CT-based attenuation map. And on the right, we show that the SPECT images, reconstructed images, corrected using the true attenuation map and reconstructed using the synthetic attenuation map are also nearly identical. Whereas when there are no attenuation map correction performed, there are obvious artifacts in the SPECT reconstructed images. So at the bottom, we show polar maps. So here is SPECT images with true attenuation map, SPECT images with synthetic attenuation map. They are really similar. And when there's no attenuation map performed, we can see that obvious artifacts are observed. So here's another patient example, and we can have the similar observation that the synthetic map is really consistent with the true attenuation map and lead to great attenuation correction performance. So we further investigated the impact of using multiple channel inputs and GAN. So here, the first row is the GAN results, and the second one is the UNet result without using GAN. It's just a UNet. And this is the ground truth CT attenuation map. And we can see that for both GAN and UNet, when we use both the primary and the scatter window as two channels as input, both methods produce results closer to the ground truth CT attenuation map. However, when we only use the primary window as the input, inaccurate body boundary and artifacts as pointed by the red arrows can be observed. And when we only use the scatter window as the input, incorrect body vessel shape can be observed as pointed by the yellow arrow. So this is expected because the primary window alone cannot provide sufficient body boundary information, whereas the scatter window alone can only provide very weak inner organ boundary information. Interestingly, when using only the primary window as input, GAN obtained much better results than UNIT, where severe artifacts were observed near the body boundaries in the UNIT results. This suggests that GAN training is able to obtain more stable results when limited information is available. So here we show the voxel by voxel correlation between the attenuation coefficients of synthetic and CT-based attenuation, and also voxel by voxel correlation between the attenuation corrected SPECT images using tools attenuation maps. And it can be seen that when both primary window and the scatter window are used, both GAN and UNIT obtain accurate results. However, when only a primary window is used, GAN clearly outperform UNIT. Here from the UNIT result, we see that the correlation deviate from the center line. So in summary, we develop a deep learning-based model for estimating attenuation maps directly and only from SPECT emission data by itself, which can relieve us from using the CT scans. The produced attenuation maps are consistent with CT-based attenuation maps and are able to provide accurate attenuation correction for SPECT images. For both GAN and UNIT, the use of both primary and scatter window as input provided more accurate and robust results compared with using only one energy window as input, although GAN is preferred with lower bias. However, in clinical application, the scatter window emission data are not always acquired. In this case, GAN is still preferred over UNIT due to its much more accurate and robust performance using the primary window only. So this work was originally presented at SNMMI and later published in a top-tier journal in this field. And we also have a US patent regarding this technique. So for this work, we demonstrated that using synthetic data can lead to better patient outcome. It can avoid the radiation dose delivered to patients and also lead to very accurate results. In the next work, I'm going to show using synthetic data in information retrieval. So this is improving neural models for radiology report retrieval with lexicon-based automated annotation. This is work I've done at IBM and published at NACO last year. So the motivation for this work is that the current neural encoders for information retrieval are mainly trained over unlabeled free text, like a BERT. It's unsupervised training. We found that they perform poorly on short and negative queries. Although supervised training can provide improved performance, but labeled dataset is very limited in real world. And there are studies to train neural information retrieval models using weak supervision. So these methods either use unsupervised methods such as BM25 or article headings to provide pseudo labels. However, these pseudo labels usually are imprecise and do not consider negative queries. And those article headings are not always available. So in this study, we propose to combine automatic clinical finding detection with supervised query sentence pair learning to improve training neural models. So on the right, we show an example of an ideal neural encoder. For example, given the sentence, there is X present in this image. So this is the sentence we want to retrieve. And query one is X itself. So in the embedding space, the embedding of X and the sentence should be closer, right? Query two is Y, where Y is a synonym of X. So also they should be close together in the embedding space. And query three is a negative query, no X. And it should be a little far from those embeddings. This is the ideal neural encoder. However, in the current neural encoder, they do not have this behavior. Here is an overview of our method. So for a given text sentence, we first apply fine-grained concept instruction using a domain-specific lexicon. In this study, we use a chest X-ray lexicon. that captures finding names and potential variants and synonyms mined from over 200,000 chest radiology reports. We use a string matching algorithm to spot the occurrence of the finding lexicon phrase and using another algorithm for the negation detection of the findings. So these fine-grained findings can be used to generate pseudo queries. At the next step, the pseudo query paired with a matched sentence and an unmatched sentence can be used to fine-tune sentence BERT using the triplet contrastive laws. So here we further use hard sampling and mega batching to improve training. Hard sampling means we mine the hardest unmatched sentence within the batch. Mega batching means we increase the batch to find the harder unmatched sentences. So let me give an example to show what it is. So for example, for a sentence lung, central vesicular congestion without overt edema, our methods first detect the relevant findings within the sentence, that is vesicular congestion and edema, and their associated negation, yes and no. And then we can form potential queries, which is vesicular congestion and no pulmonary edema. On the other hand, other sentences within the batch that mention the finding, but with the incorrect negation, or sentences mentioning irrelevant findings are used as unmatched sentences. For example, this sentence mentions edema, but it has incorrect negation. So it should be negative negation, but here is a positive finding. And also the bones and the heart, these two sentences talk about irrelevant findings, therefore are unmatched sentences. So in this triplet laws, we would like the query and the matched sentence to be closer in the embedding space compared to the unmatched sentences. So we collect the different data sets for algorithm parameter tuning, analysis, and evaluation. To be specific, the Indiana and NIH reports are data without human annotation and are mainly used for parameter tuning and analysis. We also collected CT and chest X-ray reports that are annotated by 3 radiologists with majority voting and use them as the ground truth for algorithm evaluation. So in the sensitivity analysis, we show that both hard sampling and mega batching can improve training. We also identify the best mega batching size through parameter tuning. We also have some interesting findings in the embedding separation analysis. So our generative negation labels enable us to create opposite negation queries. For example, the opposite negation query for no opacity will be opacity. Ideally, with a high precision retrieval system for a given sentence, the similarity score between the matched query and the sentence should be higher than the similarity score between the opposite negation query and the sentence. So if we calculate the distance between these two scores, ideally it should be larger than 0. Just imagine if they are 0, then both the positive query and the negative query will lead to the same sentence, right? Which is clearly not what we want. So we perform such analysis on our data sets, and our trained expert clearly shows separation in the embedding space. On the other hand, the naive BERT model or like a bioclinical, like pre-trained bioclinical BERT or sentence BERT trained on a large collection MS Markov, they all show that they have 0 distances and even negative distances, which suggests that they have a poor negation awareness. So finally, we also perform evaluation on annotated data. So our expert fine-tuned on either Indiana or NIH datasets outperforms the other compared methods by large margins. Here we compare with BM25, bioclinical BERT, and expert pre-trained with MS Markov. We can see that it's performing much better regarding mean average position and mean recall. So in summary, we propose a supervised pre-training task with automatic annotation, which can greatly improve information retrieval performance of sentence BERT on short and negative queries. And we also have a better scalability. So we can train cross-attention BERT models for further improvement when computation speed is not a bottleneck. Right now, we are using embedding-based retrieval, which has some speed advantages. But later, we can expand it to cross-attention models. Also, our comprehensive negation and finding labels for each sentence allows assembling more complicated queries that include more than one findings. Right now, we use, for example, A and no A. But later we can expand it to A and B or A without C and so on. And last but not least, we can extend our method to training information retrieval models in other domains other than medical domains. For example, we can use it in finance, law, and retail, providing the right lexicon. All right, thank you guys. I would like to take any questions.
Thank you. Yeah, let's see if there are any questions from the audience. You can either type or you can just unmute yourself. Oh, okay, here is a question from the audience. So for the first study, what kind of loss function used except for GAN loss?
Oh, let me. So here we have for the generator, we have L2 loss, which is commonly used for this generating task. And we also have a gradient loss, which is also kind of common in this field. I think that's the two losses that I use. And for adversarial loss, it's just a common GAN adversarial loss.
So it's like a combination, a linear combination of those losses.
Yeah, with some weighting parameters. I forgot the detailed parameters, but it can be found in the paper.
Okay, yeah, thank you. And then for the second study, can you please explain how to detect unmatched sentences? Is it a rule-based detection?
You mean unmatched sentence, right?
Yes.
So unmatched sentence would be because basically with our detection algorithm, we know which findings each sentence have, right? And their corresponding negation. So we kind of know the ground truth. And within the batch, any other sentences that do not mention the finding or mention the incorrect finding or incorrect negation, they are all unmatched sentences. So that's what we use in this contrastive learning loss. Yeah, you can think of it as a rule-based.
Thank you. Can you? Yeah, thank you so much. Can you go back to the previous page?
This one?
Yeah. Oh, yeah. We have one more question. Yeah, go ahead. Hello. We cannot hear you. I think there is a question coming up. Yeah. Anyway, yeah. So my question is, so this fine-grained concept extraction. I knew that if you work on such, let's say, medical text or, kind of very specific domain, so maybe like rule-based method would be really affect that much. So I'm just wondering, have you done any ablation study to see how much this part is affecting? So this domain.
So actually, this is based on our previous work. And so in that work, we have a thorough evaluation with human annotated ground truth. And it shows some very high like numbers, like 95 or more percentage accuracy. So we kind of consider that as like a good enough method for us to continue with this work. But for more evaluation results on that work, that's mentioned in our paper. Yeah.
I see. Yeah, thank you so much. I think we still have plenty of time for more questions. You can either type or you can unmute yourself to speak up. Thank you. Okay, there's one more question pop up right now. So for the first work, the synthetic images look similar to real images. However, they may contain some observable artifacts. Why they can be used to train the AI models and improve their performance?
Well, first of all, we didn't use synthetic methods to train the AI model. We used the ground truth attenuation map to train the AI model, and later it produced synthetic maps. There are some misunderstanding there. But we admit there like if you look at closely to these two images, there are of course some slight differences, right? So this is the true attenuation map, and this is the synthetic attenuation map. If you look at here, some details, they are not identical for sure. But through our evaluation, we show that when we apply them for the task of attenuation correction, it performs really well, at least good enough. You can find those detailed numbers in the papers. I think the final differences in the spectral corrected reconstructed images is less than 5%. It's like very minor differences.
Yeah.
So yeah, the goal here is not to create really realistic CT images for diagnostic purpose. No, it's not. It's for attenuation correction, which does not require that much accuracy.
I see. Yeah, it looks like the images are very close. I mean, I'm not a domain expert, but I think they look really highly similar to each other.
Yeah, and if you think that those synthetic images are generated from those like photons, they're not like this. So it's surprising that this can generate such high quality images.
I see. Yeah, thank you. Yeah, I think we have one last question, I guess. So how would synthetic data help preserving the privacy, for example, medical images and clinical records?
Well, that's a good question. So for example, when we train the AI models, we need a lot of the real data, right? Like normally, and those, for example, medical images. And if we use real medical images, and those images might have like a lot of personal information, right? We have to anonymize those images to get rid of their names and address and all the other personal informations. And we need a lot of paperwork to be able to use those data, right? A lot of consensus from the patients, which is really troublesome. But with synthetic data, we don't have to go through all the process because it does not belong to any like person, right? It does not have privacy and stuff. And such is also the case with text. For example, if you have patient reports, right? It might be like describe the patient in details regarding their personal history, like disease history and medication history and stuff, right? Those are really private data that we cannot just use. But with synthetic data, we can just generate those like if we have the red tool, right? We can just generate those radiology reports. For example, with the ChatGPT is really powerful now, right? Maybe we can make that work to generate those radiology reports that can avoid that privacy issues.
Great. Yeah, thank you so much. I think let's stop here. And I'd like to thank again for our two speakers in this session. Thank you so much.
Thank you.
So we will start the ChatGPT panel, I think in 5 minutes. So audience, you can stay in the line and allow me for a few minutes to prepare for the slides and inviting the panelists. Okay, so I think we have all the panelists join us. So welcome again to join our special panel discussion. So this time we'll talk about challenges about ChatGPT. So before we go into the discussion, let me first introduce our amazing panelists. So our first panelist is Dr. Alex Fabry. So he's a research scientist from Salesforce Research. Alex, if you want to spend some time to introduce yourself quickly, go ahead.
Hi, everyone. Yeah, I'm a research scientist at Salesforce. I work on problems related to text summarization, evaluation, generation in general, conversational summarization. I did my PhD at Yale, also on text summarization with Jago Rada. Happy to be here.
Yeah, thank you so much. Our second panelist is Professor Yu Su from Ohio State University. Go ahead.
Hello, everyone. Glad to be here. I'm Yu Su. I'm associate professor at OSU and also a researcher at Microsoft. My research is mostly on conversational AI and foundation models, the combination of which makes ChatGPT. So glad to be on this panel.
Thank you so much. Welcome. Our third panelist is Michihiro Yasunaga. So he's right now a PhD student at Stanford University. Yeah, I think.
Hi, everyone. So I'm Michi, and I'm a fourth-year PhD student at Stanford, working with Percy Liang and Yuri Lexwich. So I work on improving language models through integrating knowledge and reasoning capabilities into language models. For example, integrating domain knowledge like biomedicine or multimodal knowledge like images and so on. And I did my undergrad at Yale working with Jago Rada. And yeah, super excited to be here.
Thank you so much. Welcome. Our last panelist is Vanessa Yan. She is a staff product manager at OctoML.
Hello, everyone. My name is Vanessa. I'm a staff product manager at OctoML, which is an AI infrastructure Series C startup. I used to work with Jago and Irene on NLP research back at Yale. And right now I work on building tools that help developers deploy machine learning code into applications for production use much faster, easier, and with lower cloud costs.
Thank you so much. So I'll be the moderator today. So I am Irene Lee at the University of Tokyo right now. I'm also starting my own team here. So I'm interested in natural language processing the most, and also other machine learning applications. Thank you. So let's try to get started right now. So I'll first give you a very brief introduction, then we'll go through, I think we have 3 different topics, and based on the time, we'll see how much we can go so far. Okay, so so when we're talking about ChatGPT, obviously this is the topic for today. So when I was trying to organize this session, or I have to organize and cooperate with each speaker to ask them to what day is the best day for you to make this AI seminar happen. And then I asked each speaker, including the panelists, to submit their availability. So then I'm so shocked because we are all in different time zones and each one gave me so many options. So then I went to ChatGPT directly and I submit, you can see on the left, this is what I did ask ChatGPT. I asked the ChatGPT to give me a good advice or a good time that works for everyone. And then on the right part, this is the response I got from ChatGPT. And it actually gives me, I think it's pretty making sense. Although it's not perfect answer, but still it was helping me a lot on organizing this event. So I should thank ChatGPT for sure. Yeah, this is quite amazing. And then for the past few months, when ChatGPT came out, people are testing it in really funny way, but also in a way that it can really help us in our work for example, to help us to code, help us to translate documents, summarize document, and whatever you can imagine. And then also there are so many other tools that based on ChatGPT using maybe similar techniques And then you can see people are trying to use ChatGPT to create arts, create lecture slides, or create some other funny things. So our first topic would be potential applications and some limitations that you can imagine or you can think about. So for example, we all see that ChatGPT is really, really powerful than nearly all the previous large language models or softwares or other tools. But what are the current limitations of ChatGPT? And based on this, what do you think might be happening in the following years or in the following time that ChatGPT can do? Yeah, so I think we can just follow the order if that's okay for you. So maybe let's start with Alex. Go ahead.
Sure, I'll go ahead. So yeah, one limit of ChatGPT currently is, you give it a prompt and you ask it a question, but it's currently limited in that it was only trained on data up to 2021. So if you ask it about, what's the weather today or something, maybe it doesn't necessarily have access to that. And it still might also, even before 2021, it might have some incorrect answers. So I tried to ask it to give what it knows about Drago once as a prompt, and it said he was still at Michigan. So that's obviously wasn't correct in 2021. So obviously this factual consistency problem is still an error, still a big problem. And some ways to mitigate it are through some retrieval-based approaches. And I think a lot of people are doing that, and it's integrating that as search and as part of search engine. So that's especially the factual verification is something I'm pretty interested in. So yeah, maybe that's like a starter topic we could go with.
Yeah, that makes sense. It's really like restricting the resources that the answer sometimes is not updated. Thank you. Yeah, maybe next. Yeah, Professor Su, go ahead.
Sure. Well, this is a big question. There's just so much we could possibly say about it, so I'm not sure where I should stop. There's some obvious elephants in the room, right? Like I work at my daytime job is at OSU, but my nighttime job is at Microsoft. So I got to see all these significant changes happening from more like an insider view. It's certainly very powerful. It's revolutionizing a lot of things, but it's also limited in many obvious ways. The hallucination issue that was just mentioned, and which is rooted in some other more fundamental limitations of the model itself, right? Like the not up to date training data, the stochasticity in its inherent in the model, and so on and so forth. And it's not even, it's another interesting topic to debate, but it's not even that clear that retrieval augmentation alone would just in principle solve this issue. That's a big question mark. And then there's related to that, there's attribution, right? How to attribute the generation to the training data or to the proper places in the context, which in turn is related to transparency, related to trustworthiness, and also hallucination, right? And then another issue that is perhaps closer to my heart is a grounding. Grounding to it's fun to use ChatGPT for these general problems. For example, getting the example you just showed, or the other day, I was asking ChatGPT to reformat all of my publications, because for an application, I need to do that. And it saved me maybe 1 hour of effort doing that. That's very helpful. But the ton of real world application scenarios, what we really need is to solve tasks, solve problems in specific environments. Like if I work at the company, I would need to do my task, then all I care about is not whether it was Trump's birthday or things like that. I care about whether it can understand the specific nuance of the context in my company and in my talk for my task, and then do things, generate things according to that. So grounding is certainly something that is significantly missing right now, but there are a ton of effort also ongoing. Like for example, the two-farmer paper is a step in the right direction. Well, there's, I don't think I have time for the second part of the question, like the applications, but yeah, ChatGPT plus robotics is what we are currently doing. And there's a lot of exciting development in that space as well.
Yeah, thank you. Especially you're working in Microsoft, they have the new Bing system, search engine. We'll talk about that later in the following question. Thank you so much. Yeah, let's move on to Michihiro. Go ahead.
Yeah, for sure. So I think Alex and you made a very good point about factual correctness and also grounding and so on. And I think related to that, maybe one limitation is like the customization or personalization of language models. And at the same time, I feel like this is a limitation and also a huge kind of opportunity for future applications. So for example, right now ChatGPT is kind of often used for answering general questions like or requests, like writing emails or Irene did in the beginning, right? Like making some schedule. But there's a lot of opportunity for many kind of specific businesses, like restaurants or shops and other companies to use and customize the language model for their own purposes. And right now, the language model can already, or ChatGPT can already handle this. So for example, let's say I have a restaurant and I have my own, custom database, like, menus and, the table information and so on. And I want to set up, a chatbot that is customized for my, database, right? And it can answer any customer questions like, oh, does this pad thai contain, peanut or not? Or can I make a reservation for 10 people or things like that? So I think, yeah, so those small businesses and companies, they want to set up their own chatbot instead of the generic ChatGPT. So I think that there's a lot of opportunity to kind of customize and personalize those language models for specific database, specific domains in an efficient way, because there are so many different people's having different interests in retraining models or retraining like a chatbot for themselves is very expensive. So how can we quickly adapt ChatGPT for those personal custom use cases? It will be a very interesting application, and also at the same time we need some work to make that happen.
Thank you. Yeah, I think this is a very interesting point. We all wish that this kind of thing can really affect our lives, can help us to reduce some labor works for us. Yeah, I think this is really like a very possible and useful suggestions on this. Okay, so yeah, Vanessa, go ahead.
I see two limitations of ChatGPT right now. The first is cost, and the second is customization, which Michi already touched on earlier. Well, it's actually very expensive to run large generative models like ChatGPT in production at scale. While working at Octomel, I see developer teams come to us saying they're spending millions of dollars per year just running the model in production, like not even counting the cost for training or fine tuning. And obviously not every team can afford to do that. Not every lab can afford to do that. So, actually commoditizing the compute layer underneath to make sure people can actually iterate on these models and run them in production in a actually cost effective and feasible way is very important. And furthermore, if you're trying to use a kind of closed source generic API for these models that another company has pre-built, you end up having to pay an extra cut to that API provider. And again, that's another lever for cost. And furthermore, if you're using someone else's closed source API, you don't get to do the kind of customization that we talked about earlier, right? You need to find a way to make sure that you can make the model actually work for your company's or your team's use cases, your data, and what your users actually need. So that's why we recommend the teams that work with us to pick some open source equivalents of these models, so that you can actually inspect the code, modify it to your use cases, and then at the end of the day, use automated tooling to make production grade APIs for your customized version of these models.
Yeah, I see. This is really like, I think as AI researchers or NLP researchers, this is also the same problem that we're all facing. We're not large labs. We don't really have the so many like, the HPC things to help us to support our research. And this is definitely a challenge for us too. Yeah, we'll talk about that later as well. So anything you want to add from the panelists? Or if not, let's just move to the next question. Okay.
Maybe one more
Yeah.
limit. Oh, sorry.
Go ahead.
Maybe
Go ahead,
one more
Missy.
additional limitation might be the uncertainty kind of quantification. So right now, for example, we talked about the phenomena where ChatGPT just hallucinates and fails if you ask some question that require knowledge, especially like domain-specific knowledge, like medicine and so on. But the model actually, when it fails or hallucinates, it can give the wrong answer in a very kind of confident way. So, for example, if you ask, oh, does butterfly have like 4 wings or something? And the model says a butterfly should have 2 wings in a kind of confident way. So how can we ensure the language model outputs the answer in a kind of more calibrated way? If the language model is uncertain about some of the particular domain knowledge or factual knowledge, it should just say so, I'm uncertain. And if the model is like very certain, you should, say, yeah, this is certain. So I feel like this uncertainty quantification is also very, very important, especially if we want to apply language model ChatGPT in a high-stake domain, like a biomedical prediction and so on.
Go ahead.
Yeah, I'd like to follow up on what Michi said about 2 things. The first is about customization, which Vanessa also said. I think Sam Altman once made a remark that I fully agree with. Like language models are here to stay, and likely the future landscape will be like there are a few like T0 players who can train these very large language models and provide service to others. And then there will be these T1 players who like fine tune or customize or provide some easy-to-use platform based on these services from T0 and then provide value to customers. And this is really the T1 layers has tremendous like research and entrepreneurship like opportunities.
Yeah, totally agree. Right. Okay, let's due to the time interest, so let's move to the second topic. It's more about AI ethics. So right now, on the image you are looking at, this is actually what I did. What I made using the Midjourney. So I asked the robot to generate an image by giving this prompt: 2 cats are surfing on the sea. I think this is really funny, and actually the image, personally, I like it very much. However, this brought me to our, brought us this following question. So such generation models, including ChatGPT, what we can do about the copyright? Am I allowed to sell this image, or just use it for such seminar, or like use it publicly? And then another point is that it's on the news all the time about that college students use ChatGPT to do their homeworks, or even doing something by using the power of technology. So far, maybe not every university has conduct any guidelines or policies of using ChatGPT. And then finally, how should we build a discipline of applications by on the usage of public or education? Okay, so yeah, maybe Alex, you want to start?
Sure. Yeah, so I thought the question about copywriting output was pretty interesting, and I was trying to look what the current rules are for general AI, AI generated work. So, apparently, like the work must be the result of original, like to quote, original and creative authorship by a human author to be something that can be copyrighted. So you couldn't copyright your ChatGPT output, which I think is interesting in some respects. Like one person you know, compared it to a graphic designer who uses, let's say, some program to, you know, design something, and that you can, you know, copyright that design or some that you make, but yet you can't do that for, you know, this sort of output. So I don't know, I guess, you know, I don't know if there will be any changes, but I think just thought that was an interesting point. And also, I guess for the education, I think it's quite interesting. So New York City has, I think, banned the use of, you know, ChatGPT as an assisting for work, and I think probably other schools will follow it. So I mean, I think it could be like a very good educational tool. So I like hope it just they come up with some regulations that could be useful around that. And then, yeah, just one final point. I thought it was quite interesting how, you know, you see these articles on ChatGPT, how it is able to perform well in like law school or certain, you know, exams. So maybe I think it got like a B on some Wharton UPenn exam. So I mean, I think these things sort of tend to move slowly, but it'll be interesting to see what sort of regulations. I don't know, you know, where we'll go from here, but I think it should be like a useful tool in education. So hopefully it just doesn't get completely banned.
Yeah, I agree. I think it's really like a very good tool for education, because sometimes I use it to improve my bad English too. So yeah, let's move to Professor Su. Go ahead.
Yeah, these also very tricky issues that we kind of have to think about every day almost. So for copyright, I think for image generation, it's trickier because it's harder to trace like the source. But for text generation, at least I hope we could do better by a combination of attribution. And so whenever the language model is using some source, either like citing from its training data or citing from the retrieved information, make explicit citation in the generation. And whenever the language model is making any sort of extrapolation from this existing information, in the generation, the language model should be explicit about that. So then if we can have like this combination of things, then one day maybe we'll have this language model generation where everything can be traced back to like, you know, why it's generated that way. So then if we can achieve that through technical advance, then copyright on the text side will become easier, I believe. But currently it's not clear how to achieve that yet. I hope maybe people here will work towards that. For education, yeah, that's another big issue. I was called to our like university president's office to specifically chat about ChatGPT, and part of the topic was what it means for higher education. Different people definitely have different opinions, and there are already like multiple universities across the world who have explicitly banned ChatGPT use on campus. Personally, I think, of course, language models are here to stay, so we have to learn to adapt to that. We could do things like there could be regulation, like especially a combination of technique and regulation. For example, watermarking, that could be technically possible and could be like enforced by regulation. And also like as educators ourselves, we should adapt, right? We should probably now we can like just stop doing this kind of just memorization or like simple calculation type of homeworks, but more like more creative homeworks. And also like then once we did our due diligence, I think ChatGPT presents more often opportunity than a threat to education, right? So now it's more, you can think of it as like a personal 24/7 kinds of co-pilots for students, right? So they can ask chat about what they're learning. They can get feedback anytime, and maybe, for example, homework can be designed in a way that students should criticize, have a conversation with ChatGPT about a certain topic and criticize the positioning of ChatGPT. So I think that there's a wide space of possibilities. So very excited to see what will come.
Yeah, thank you. Similarly, as an educator, I'm kind of worried that students might use it to, just to make up something. For example, if I ask them to write something, then they may use ChatGPT, and unfortunately, I may not able to distinguish if they wrote themselves or if they use ChatGPT to do it. Though I think OpenAI has released a model to try to help you on classifying if this is generated or not.
Yeah,
but
that doesn't work very well.
right, yeah, but that's not really the case. So yeah, it's like, so it could bring, very bad situation that people, but maybe students use it to write papers, and and on Twitter, people are discussing about this too. I think ACL has announced that we're not allowed to use ChatGPT for any paper contents, but then there's a comment saying, how would they know? So this is really sometimes very interesting that we don't really know what to do, and we don't know how it would be like in the future. Yeah. Okay, so yeah, let's move on to Michi. Yeah, what do you think about this?
Yeah, I feel like this is a very interesting topic, and I think Alex and you already made a very nice points that most of them are kind of already on in my mind. And yeah, so I feel like for copyright, maybe I agree that having some watermark or developing model marking techniques is a reasonable way to go. So for example, in the kind of text to image generation kind of the literature, people are also investigating a way to kind of inject some invisible kind of watermark into model generated images, so that you can detect, oh, is this image generated by the AI model or else, and maybe setting up some regulation to enforce this kind of practice might be useful. And also for text, yeah, I think already people mentioned, but there's active research in trying to develop watermarking technique. Like I think the OpenAI thing, and also there's a GPT-0. Detect GPTs, things like that. So hopefully this kind of watermarking technology will improve in the future. In terms of education, yeah, I'm also trying to think about that recently, and maybe I'm not sure if this is a good analogy, but for example, right now we use Wikipedia and so on, right? When we as a kind of inspiration, maybe when we write some text and so on, but we are kind of the practice, like we need to make sure, okay, we make the references explicit, so that here's what we read from somewhere else, and those are references, but here's what I've came up with in a new way. Like this is the part we are creative about, right? We need to make this explicit in our homework or paper and so on. So maybe ChatGPT and so on will just be kind of this kind of tool where you can draw some inspiration, but at the end of the day, you're expected to write things on your own words, or you are responsible for the content you wrote in your paper or homework and so on. So I think there's definitely need to develop this kind of regulations, but in the long run, probably language model will be just a kind of tool, and humans kind of we're expected to be kind of more creative and find a way to use this language model as a tool and come up with our own value in the papers and so on. So that's my current feeling.
Yeah, thank you so much. So far, I don't think my university has came out any regulations for this. Neither do I know how many of the students are using it. So I do think we need some time to observe more and then try to see what we can do in the future. Thank you. Yeah, Vanessa, what do you think about this?
Well, I think the other panelists made really good points about copyright and education already. So I'll try to come at this problem at a slightly different angle. In terms of ethical issues, what's top of mind for me is actually the explainability of these models to the broader public. and how to get the research and open source community very involved in how these models are built and what kind of outputs they create. Currently, I would say a few very large companies are controlling most of the training and implementation of these models, especially the foundation models are really large, right? And some companies open source their models, but not all do. And that's a little concerning, because without the public and the open source community kind of come into verifying the implementation and the methodologies, we can't really verify as the public audience that these systems are built in a way that's very ethical, and in a way that's explainable and beneficial to all of humanity. So that's something we should keep in mind, because more and more applications are built on top of these large models now. And as all of the world starts to rely more and more on the outputs of these models, we should make sure that the public also has visibility into what led a model to say what it says in the first place, and have a way to kind of give feedback on that, and not just kind of have it entirely be a black box.
Yeah, totally agree. I think, yeah, if the model is really like huge and it's generating some outputs without any explanations, I feel like I would doubt if the generated results it's true, or I would like to know the source of it. And the new being kind of I think it's kind of doing that. So it gives you some resources, or sorry, the bibliography or whatever. So it would show you the source links or URLs. That kind of, to some extent, I think that's really helpful for those for me to check the outputs. Okay, so right now let's see anything anyone wants to add or follow up based on ethics. Any panelists, anything? Yeah, okay, so I thought, yeah, Drago, are you able to unmute yourself?
I'm unmuted.
Oh, okay, yeah, go ahead.
No, I was just asking, you mentioned that ACL doesn't allow text written by ChatGPT. Is there some link for that?
I can look for that offline, but
No, let's do it offline. I don't want to disturb you from the presentation.
Yeah,
I think ICML made that explicit.
sorry.
ICML this year.
Yeah, I've seen different announcements, but nothing from ACL, and it's good to know.
Yeah, might be a mistake. I mean, yeah, but I do saw like something they're making this like preliminary discipline on this. By the way, one more thing. So is Yale University making such rules or restrictions on using ChatGPT?
Yes, actually, there was something that came out recently. I'll forward it to you right now.
Okay. Yeah, in University
and then you can decide what to do with it.
Yeah, I don't think every university, I do believe that they have something within their own university, but there is no standard discipline that everyone is following. So I'm just curious on like what the top universities are doing right now. Okay, yeah, let's maybe move on to the next topic. Yeah, so this is basically some we wish to discuss on some other new challenges that we haven't discussed so far. So here are some possible topics. Like what do you think are other possible changes when ChatGPT came out? And maybe what are the next generation of search engines you see? And the last topic, this is very interesting for me, is for NLP researchers, what we can do. We cannot fight with the top companies by ourselves. So what's your opinion on this? Yeah, Alex, go ahead.
Yeah, I'll start with the last one, the NLP researchers. No, I think it's an exciting time to do research. I mean, I think, yeah, trying to compete with them in terms of training models is, I mean, that's sort of been a problem for I mean, now it's maybe becoming a larger problem as the models get larger, but it's also been a bit of a problem for a while, even like, and like as PhD students struggling to, you know, find the GPUs to train the models. But I think that like in terms of model analysis and like running studies and understanding these models, I think it's like we have so many new tools, like, you know, a new model comes, a new version of Flan comes out, and the next, you know, then it's on Hugging Face, and then, you know, you can just analyze it, see what it does well, what it doesn't do well. So I think I'm very excited for that. I think just better understanding these models, and also just like for ChatGPT or GPT-3, you know, not to require, if you know, have some budget to make the API calls, which are fairly cheap, you can, without a GPU, do a lot of very interesting analysis, which I think opens up possibilities that, you know, previously you would need to, you know, set up all your models on GPU, you know, run inference, make sure it's set up, and that could take a potentially a really long time. But now you can just maybe make an API call, and then you can already like, you know, start some analysis. So I think that barrier to entry is quite, you know, that being lifted is quite nice. Yeah, and I guess, yeah, I guess that's what mostly I'm focused on. I guess, you know, for as far as applications, it does, like, and being at a company, it does, you know, pose some challenges. Today we just announced like an Einstein GPT, which is a partnership with OpenAI, and we're also like developing our own model. So that becomes a bit more challenging in terms of applied research, but I think in terms of general NLP research, I think it's an exciting time. I'll just stop there.
Yeah, thank you so much. Yeah, I've been actually thinking like what we can do, because I tried to see like how expensive the open API, especially the ChatGPT API. And then I think it's like, well, for $100 you cannot really achieve that much. But recently they're reducing the cost. I think this is a really good indicator that we can do something in a more cheaper way. Yeah, thank you so much, Alex, again. Yeah, Professor Su, if you can share your opinions on this, go ahead.
Yeah, maybe I can follow the reverse order as well. So for NLP researchers, I think we're far away from being done. In fact, I think it's the best time ever to do NLP research. Like I started doing NLP research before foundation models, even before neural networks becoming popular in NLP, right? So I still remember in the older days, I would need to, well, do a lot of syntactic analysis and some other sorts of analysis, and then extract the features, and then so that we can do machine learning for NLP tasks. It's not because I like to do syntactic analysis, right? So that I had to. But what I like to do is to focus more on like higher, like more intelligent tasks. So now with these ChatGPT or the foundation models like this are really like just much more powerful kind of tools that so that I can focus my energy on like more interesting things that were not possible before. So for the next generation of search engines, I need to be a bit more careful here when talking about Microsoft stuff. So I think it probably won't be very viable, like just replace our current search engines in the near future. And the part of the reason is that there are just a lot of like search traffic that don't really need ChatGPT. Another reason is really about cost that Vanessa mentioned earlier. This is not from insider information. This is just my best guess, but my best guess is that both Microsoft and Google click on every search query, right? So it's totally fine for Microsoft because the market share is of Bing is not that large, but it's a very bad thing for Google. Well, because they are forced to defend their business, their core business. That's part of the reason why like Google's stock price suffered that much. Not mainly because that factual error that the media like to pick up. So I think before we can, before like we make the hardware good enough and before we optimize like the entire stack well enough so that the cost becomes manageable, I think that we probably won't see like just an entire search engine being powered by large language models. And I think currently Microsoft and Google both only offer like a limited access to their new version, right? But we will see a lot of more applications, truly like widespread applications on some like more high margin tasks. Like search is like a pretty low margin task, right? Like every query, every traffic that just brings a very small profit. But there are many other like high margin tasks that could truly be like revolutionized by these models.
Right. Yeah. Thank you so much. I also agree with you on like the traditional search engines, they may live longer than we expected. I'm actually expecting what a good search engine could do, especially maybe at the current time, I wish the ChatGPT part can also integrate multimodality, for example, maybe generating images or videos or whatever the current traditional search engine could do. So I see some of the changes right now. So I think maybe it's the Meta. So they released the Cosmos 1. That's the like very large multimodality large language model. So I'm really exciting to see like what we can have in the near future for the search engine, especially. Yeah. So Michi, if you want to continue on talking about this, go ahead.
Yeah, for sure. So I think, yeah, this is a very exciting time for doing research in NLP and like kind of AI in general. So maybe I can talk about two kind of interesting challenges or opportunities of research. So one thing is the efficiency. I think people already brought this up, but recently I had a chance to kind of talk to a couple like startup companies and so on. And they are very excited about trying to use something like ChatGPT for their private data. But due to privacy reasons, those many companies or institutions, they cannot just use the ChatGPT API. So ideally they want a local model that works well and that is adaptable to their custom domain. But ChatGPT is too big and it's also not available for download, right? So they want to hopefully have their own kind of local model that can perform ChatGPT level performance, by using much smaller model size or fewer compute for training or inference. So I think there's a lot of interesting research questions, opportunities for improving the efficiency of those language models, right? How can we achieve ChatGPT level performance much more efficiently? So for example, the RLHF is kind of a secret recipe to get a high quality language model, but it requires a lot of human annotation as well. So can there be a kind of way to do this kind of RLHF in a more efficient and open collaboration kind of manner, or can we just do like in a fully self-supervised way, like the constitutional AI paper that came out recently? There's also like a recent work from Meta, like Llama, where they can achieve very good performance by just training like a smaller language model. So I think those kind of efficiency topic is a kind of good research direction to pursue. And hopefully academia people can also work on that because, ideally you want to have an efficient model that can be trained in academic budget. Another kind of a research direction I'm personally very excited about is kind of multimodal ChatGPT or multimodal kind of personal assistant. So right now, ChatGPT is pretty fluent and can give us a lot of kind of advice or answers when we ask questions, but everything is in text. But what the world we experience as a human is highly multimodal with language information, visual information, audio information, and so on. So it will be very, very cool if we can have a language model or like a multimodal language model where the input and output can support any sequence or mixture or combination of text and images and audio. So this will be very useful for chatbot application. For example, you want to build the customer service chatbot, and probably the customer maybe have some issue with the product and they want to ask a question, and then maybe they want to take a picture of their product and ask a question, oh, what's wrong with my product, and so on, right? So hopefully you'll be able to not just ask question in words, but also showing the visual information and so on. That will be very, very useful. So personally, I'm these days kind of working on this kind of multimodal language model as a kind of exciting research topic. I think there's a lot of challenges here, like how do you want to represent text, image, or audio in a kind of a coherent representation in the same space and so on. So there's a lot of a research question here, and I'm very optimistic about the research avenues in this era.
Yeah, thank you so much. Yeah, let's move to Vanessa. Go ahead.
Yeah, I would say rising tide lifts all boats. What OpenAI has done for us is direct the world's attention towards AI and make it very relevant for the whole world, right? And what happens in industry now is a lot of enterprises are directing a lot of their existing resources more towards the AI orgs, including for both the research folks and also for folks who are trying to build applications around these AI models. I sure hope the same happens in universities and the research world, right? Like, as AI becomes more and more relevant, we need more resources in AI related departments to do further research. So, with additional funding, I think that's helpful for folks to go find new directions to work on. And, that cost efficiency challenge is definitely something on my mind. It remains an unsolved problem. And there will be lots of advances coming in the next few years that helps folks iterate on training, fine-tuning, customization, and running inferences in production, all in a cheaper way. And that should enable the research and open source community to go build more stuff on top and play with different models, try whether different approaches could solve certain tasks better. And I find that very exciting. I think given all the resources that are coming in, and also how the cost problem is interesting to many people now and will continue to be in the future, I think we'll be in a good spot to be empowered with the tools we need to do more research and keep advancing the state of the art.
Yeah, thank you so much. I think we have to stop here based on our tight schedule. I would like to thank again for all of the panelists to share their opinions. They're really helpful and inspiring. Yeah, thank you so much. So yeah, we did not have time to allow more questions from the audience, but thank you again for doing this. Okay, so now let's move to the second session, which I believe we'll talk more about natural language processing here. So we have two speakers. They are also from the panelists too, Dr. Alex Fabry and also Professor Yusu. So Dr. Alex, if you can go ahead and share your screen, start your talk. Thank you.
Sure, 1 second.
Yeah, so the panelists, you can turn off your cam if you wish to. Thank you. Go ahead.
Okay.
Are you able to share? I think you can.
Yeah, I think it's 1 second. Okay. 1 second. Oh, it's asking me to quit and reopen one.
What about now? Can you try? Yeah, let's wait for maybe a minute for Alex to prepare his slides.
Hi, Irene, sorry about that. Yeah, so here,
You? Are you able-
it says disabled participant. Oh, could you add me as a host again?
Go ahead. I think it
Yeah.
works.
Okay. All right. Can you see my screen now?
Perfect.
All right. Hi, everyone. So, yeah, again, I'm Alex. I'm a researcher at Salesforce, and we'll be presenting this talk, revisiting summarization evaluation, a novel benchmark, and a study on opinion summarization. So just for some small background, as we know, text summarization is a process of distilling important information from a source or sources to produce an abridged version for a particular user and task. And this talk will focus on summarization evaluation. Summarization is typically evaluated with respect to reference summaries, which are gold labels. And a common way to do so is a common metric is Rouge, which measures lexical overlap of the model summaries with respect to these reference summaries. However, Rouge has known limitations, as a reference summary, as the one seen on the screen, might have high overlap with a summary lexically, but may mean something different in the case of the summary on the bottom left. And while there's automatic evaluation with some problems, human evaluation, even though it's the gold standard, is often expensive to collect. So there are some issues with both of these settings. In general, summarization evaluation is an important task. Properly evaluating systems is essential to correctly rewarding and choosing models for production. Furthermore, being able to detect good and bad output, either in model selection or in displaying model confidence, whether to show a summary, can have some serious implications, serious financial implications or others. So with that background, I'll actually start the talk with the opinion summarization work. This is work called Prompted Opinion Summarization with GPT-3 in collaboration with Greg Durrett at UT Austin. To give some background on opinion summarization is the task of summarizing opinions of typically online reviews. The two main data sets that are used in this area are Space, which is for hotel reviews, and FewSum for product reviews. Space is aspect-based summarization, where you summarize with respect to a specific aspect in the input, such as location or food, while FewSum is a generic opinion summarization data set. As you can see, the data sets can differ largely in input size on the right. So the Space data set contains over about 100 reviews and can be quite large. In prior modeling approaches, there are extractive approaches where we just extract a subset of the review sentences based on BERT, for example. There have also been several abstractive models, which we will later use as the foundation of our analysis, such as ASUM and FewSum, which is also the model introduced in the dataset paper. So with that background, in this work, we address two main questions. One is whether the strong performance of the large language models, which we've been discussing, extends to the task of opinion summarization. And the second is whether the current automatic and human evaluation approaches are able to accurately measure the performance of these large language models. To give a high-level overview of our contributions in this work, we examined several novel pipelines for GPT-3-based opinion summarization, including hierarchical summarization, where we recursively chunk and summarize input, as well as an extractive and abstractive two-stage approach. We compare with prior models using automatic and human evaluation. And we propose several entailment-based proxy metrics to better capture faithfulness, factuality, and generosity in opinion summarization. So since we saw that the summarization data sets such as space for opinion summarization can be very long, we need a pipeline approach to process the entire input. I'll now introduce the components of the pipeline, which will make up the models that we study. So here each has a letter representing that component. For the T component, one thing we do to deal with the input size is to cluster according to topic, and then only take the topic sentences which are relevant to a particular aspect. In another setting, review-based, we cluster sentences according to the reviewer score, which are present in the dataset. In an extractive-based approach, two-stage approach, we first use the QF sum model mentioned, and extract sentences for the second stages. And in the chunk-based component, we apply GPT-3 to produce chunks of non-overlapping sentences, and then do this recursive summarization approach. And these pipelines can then be combined into these components can then be combined into several pipelines. Here is a list of the different pipelines that we test on the space data set. You can see we can first apply topic clustering and then chunking and generation. And then similarly, we have these components for FewSum. There are a few less pipelines as this is not aspect-based. So here's an example of one opinion summarization pipeline that we analyze. The sentences are first on the left clustered according to classified according to topic. Then the relevant topic at the top is then input for the chunk summarization component. We're left with then two summaries from GPT-3. And then finally, in the final stage, these summaries are combined for the final summary for this aspect-based summary. That's just one example of a pipeline. We also have all of the other combinations of pipelines. So first, we came up with these pipelines, and we wanted to see how the pipelines performed according to automatic evaluation. We do some standard metric reporting using Rouge and BERT score, and we find that the baselines outperform our GPT-based pipelines by a large margin, as you can see. The ACE-SUM model, the first two lines are the non-GPT models, and the FewSum on the FewSum dataset performs best. But this doesn't paint a full picture of the results. So if we look at this example on the right, we have a reference summary followed by an extractive summary, the ACE-SUM summary, and then one of our pipelines. You can see the style of the output is quite different, obviously between the extractive model and the abstractive model, but also between ACE-SUM and GPT. As you can see, there are certain words such as overall or some reviewers noted, and these aren't found in the references, even though they're just normal additional words, but they would be penalized as they are not found in the reference and thus do not overlap in the case of Rouge. So our initial qualitative analysis suggested that these metrics aren't capturing the quality of the GPT-3 summaries. So we wanted to see how these automatic results compare against the human evaluation. So specifically, we measure several these 4 dimensions. One is intrinsic factuality, which is whether the summary accurately represents the popularity of an opinion. This is a sort of opinion quantification, or how many people believe in opinion. Then we also do extrinsic factuality, which is whether the statements have some support in the input. This is whether they are supported at all, or whether they are just completely made up. We also analyze faithfulness, which is whether the viewpoints are the consensus viewpoints. So this is whether the model correctly chooses the viewpoints that it should represent because they are quite popular in the input. And then the final one is relevance or salience, which is whether the points raised are relevant to the aspect, in the case of aspect summarization, that we are interested in. We did a small scale annotation of 50 summaries for each of the 2 data sets, and then 3 expert annotators. So for the space data set, which as a reminder is a longer input and has aspect-based summaries, we find that the models score fairly similarly on factuality and faithfulness in general, but the GPT-3 models do perform better in terms of relevance. We also note that there is a fairly good inter-annotator agreement as measured by Fleiss kappa. And just for references, you can see the maximum score. These are Likert scores 1 to 3, and then 1 to 5 in the latter 2 columns. For FewSum, the results are a bit less clear, as the annotators, as you can see in the Fleiss kappa row, they are struggling to reach a higher agreement. And this points to some of the differences between space and FewSum, which we'll also return to in the second part of the talk. So FewSum is a generic non-aspect-based summarization, and that makes the task of evaluation less constrained. So that makes it harder for the annotators to agree on what we're actually measuring. We do see some improvements in faithfulness in certain GPT-3 pipelines, though. So up to this point, we looked at the automatic evaluation. We found that it didn't think that our GPT-3 models were best. We found some differing results with the human evaluation and our qualitative analysis. Now, what we do in this work is we try to propose some proxy metrics that will sort of better capture the dimensions that we wanted and that we analyzed in the human evaluation. So on the right side, we show how we break down the summary into simple sentences via GPT-3, and then we calculate the entailment score with respect to each source sentence. So this is trying to see whether the summary sentences are actually supported by the input. And then we can use this factor, whether they are supported or not, as a proxy for these faithfulness metrics we're interested in. So these, we use these entailment scores as proxies. For faithfulness, we use whether the number of source sentences with a score above a threshold. For factuality, we just want to see whether there is something which entails it. So we use the top entailment score. And something we're also interested in is whether the summaries just simply produce a generic output, which is sort of naturally faithful and naturally entailed. We have this proxy for genericity, or how generic these sentences are. And basically we check whether there are many summary sentences from the model or from the summary of other other summaries that actually entail this summary sentence. Whether this current summary sentence could be entailed by other summaries, which shows that it's not specific to this input. So looking at some results on this proxy metrics, we find that, and in this table, we have this column which shows how many sentences have a support above a threshold. We see that the ASUM is scoring quite well on factual consistency, which did align with our human evaluation. But if we look at this genericity score, ASUM is actually also the most generic, has the most generic output. We find that the GPT-3 model, in general, when we apply these pipelines, the GPT-3 model does degrade in performance a bit when we apply this recursive summarization. So, for example, the first TCG, which just is a pipeline which applies only once, this output, this GPT-3 model only once, as opposed to recursively, actually had a slightly higher faithfulness score. But in general, I think what we want to know is that these proxy metrics do, improve, obviously, compared to something like Rouge, but there's room for improvement. But I think in general, the spirit of this paper was just to show that we should strive to evaluate with respect to these dimensions that we're interested in. And yeah, just to conclude this part of the talk, we overall show how GPT-3 can be applied to opinion summarization. There wasn't necessarily a model that simply outperforms all others in each aspect, but rather we focus on understanding the need of human and automatic evaluation to be more targeted for this task. And here are some sort of open questions that we have based on this work. How can we sort of more reliably evaluate this factual dimension, especially when we're dealing with such long inputs, and also there's a lack of data to sort of verify our metrics on, and also scaling these evaluation metrics to maybe specific cases of factuality, or which might require some in-domain data. So yeah, let's just conclude this part of the talk. I can go on to the next, unless there are any questions that anyone wants to interrupt at this point. Okay. So next is this work we have under submission called Revisiting the Gold Standard, Grounding Summarization Evaluation with Robust Human Evaluation. So in our previous work, we just saw that there's a need for targeted evaluation that specifies, that targets certain dimensions that we want to evaluate. And this is also in a similar spirit. In this case, we focus on developing a human evaluation protocol and not the automatic evaluation. So as we discussed, human evaluation is essential for model and metric development. However, performing a human evaluation is not always straightforward. So annotators often disagree on what is a good summary, and crowdsourced workers don't always produce high quality annotations. Furthermore, it can be difficult to draw statistically significant conclusions based on current evaluation dataset sizes, which are often constrained by a budget. So in this work, we try to improve human evaluation protocols for summarization. In particular, we propose an improved way to collect human judgments of summarization salience or relevance. We then use this protocol to collect a large benchmark consisting of 22,000 summary level annotations. And this required over 150 hours of manual in-house annotations. And then given this benchmark, we want to better understand how this relates to current protocols and their biases, and we do some analysis on how we can move forward with summarization evaluation. So to start, we introduce this ACU protocol. So we want a protocol that will allow our annotators to objectively judge whether a summary contains salient information from a reference summary. So to do so, we develop this protocol where we first take a reference summary And then we asked the expert annotators to extract simple facts or atomic content units from these reference summaries. Then, given a system summary, we do a matching phase where the annotators will check whether the atomic content units are present in this system summary. So here you can see an example of a unit, Chelsea weren't awarded a penalty, which is present in the system summary, so that gets a check mark. This is by breaking down the task into this ACU writing and ACU matching, we're able to more objectively determine the information overlap between the reference and the system summary. And we'll show that this gives good annotator agreement. So our benchmark is called ROSE. It's we collect these ACU annotations across state-of-the-art systems on news domain as well as dialogue domain. And you can see we have a high Krippendorff alpha of 0.75, which is quite good for summarization annotations. And just a note, as you can see, we have test sets of around 500 examples. Standard data sets for summarization include about 100 documents, but we have 5 times as many, and we only include state-of-the-art systems, which allows us to draw stronger conclusions about differences in system performance. So in this chart on the bottom right, this is just showing how you can increase the statistical power or your ability to draw statistically significant conclusions on system differences by increasing the size of the data set. So our ACU score is a recall-based score, checking whether the information in the reference is present in this summary. We also propose a normalized score based on ACU, based on BLEU score, and we to act more like an F1 measure. And here are just the sample scores from various systems that we analyzed. And one thing just to note between our ACU, normalized ACU and length is that the systems that we analyze vary a lot in length, but this isn't always captured in other metrics, which we thought was an interesting finding. So we have this protocol we want to analyze against other common protocols for summarization and evaluation to understand the differences. So we compare against 3 other protocols. We have ACU, which is ours at the bottom. We first analyze against prior, which is the annotator just sees the summary and doesn't see the document or the reference. In the ref-free, the annotator has access to the input document, but not the reference. And then ref-based, they have access just to the reference. So what we do is we collect annotations over 100 examples for these protocols and then calculate the correlations between protocols. As you'd expect, the prior and ref-based correlate highly with each other. But what's also interesting is that these 2 other protocols correlate highly with input length, which is suggesting that the annotator may be relying on this when they are annotating and not the actual salience of the summary. So we perform a similar comparison of these protocols, but with a focus on the most recent BART and BRIO models, which are supervised language models that you fine tune, and the zero-shot LLMs of T0 and GPT-3. We find that GPT-3 does better on the protocols where the annotator does not see the reference, as it's not trained to produce such reference summaries. And as other work has similarly found, the references aren't necessarily favored, and they receive a fairly low score. And again, returning to this part about length, if you take the prior ref-free scores, those can be improved just by If you just take for each of these summaries, take the longest summary and take that score, you can get a better average score overall. This is showing that length is actually playing a role in these other annotations. So finally, another sort of interesting fact was that we find that the annotator's prior score, so when they only see the summary and nothing else, is a better predictor of their own reference-free score compared to using the scores from other annotators. If you calculate the correlation between the prior and the reference-free score, it's 0.4, while the correlation between the reference-free score and the score from other annotators is around 0.2. So this suggests that the prior preference of the annotators influences the score when they're doing this reference-free annotation, even though they have access to the documents. So their prior preference might just influence their scores for other protocols. So this is pointing to some potential downfalls that especially when we're using these LLMs and sort of training them to match human preference, that maybe our evaluations are also sort of being biased. So overall in this work, we suggest that we use a appropriate human evaluation protocol for a given metric. So using reference-based metrics for reference-based evaluation. And also that you should carefully choose your protocol and make sure that it's really evaluating what you want it to. We call for a sort of targeted evaluation and specifying the characteristics of the summaries you want. And there are also several questions based on how we treat target length given its influence on these non-reference based evaluations and large differences among system lengths. At some point in summarization, we had length budgets. And also it's like the second question is, how can we do reference-free evaluation for things like factual consistency? So I've always been a fan of aspect-based or query-based summarization, which allows you to more constrain the task. And that also leads to better agreement in general. And if you can sort of break down the task into smaller, more defined parts, that helps human evaluation. Just to close, in this talk, we show first how GPT-3 can be applied to opinion summarization, and then we develop some automatic metrics for that. And the second part, we show that we still need this human evaluation, and we need to improve our protocols for that. And in general, in both, there's a lot of room for human evaluation and improvement. So it's an exciting area of work. Yeah, thank you. If there are any questions, maybe we have a minute.
Yeah, thank you, Alex. This is very interesting and inspiring. So I think we only have time for maybe one possible question. So either from the audience, you can type or you can just speak up. Okay, so I have a really quick question. So for the ACU protocol, are you defining like a template to doing that, or just they're free to write whatever they want?
Yeah, we have a template. It's similar to like there was this light pyramid, paper, and it's basically it should be like an atomic unit. Though like there is some freeway, like there's some leeway in terms of like how they write it, the actual, but it should just be a very simple fact. So there's not too much variation.
I see. That's very interesting. Yeah. Yeah, I'm sorry, I don't think we have time for more questions. But thank you so much, Alex, for sharing this.
Thank you.
Yeah. Yeah, thank you.
Thank you.
So maybe Professor, our next speaker is Professor Yu Su. So you're free to, I think you're able to share your screen directly. Back to you.
Yeah, let me give it a shot.
Yeah, I can see it.
Can I see this?
Yep, perfect.
Great. So I'm not sure whether I can see hands during the talk. So if you have any thing, just interrupt me anytime. Okay. Yeah, very glad to be here. I'm Isu. I'm a distinguished assistant professor at OSU. I led the NLP group here, also a researcher at Microsoft. So today I'm very glad to be talking about a topic that is really close to my heart. That is about how to ground these language models to real-world environments. Okay, let's get started. So a disclaimer that I just got time to put these slides together today. So my apology if I didn't get time to put enough jokes into this as I typically do. So bear with me on that. And if I stutter a little bit. Right. So we're really living in an era where language models just seem to nail everything. Right, like on all these leaderboards, like starting in like 2018 when BERT came out, like virtually by the end of 2020, virtually every NLP problem and the state-of-the-art model is based on the BERT of some sort, right? And then we just had ChatGPT, which is now being called ChatGPT was released in December 2022, right? And it's now being called the ChatGPT moment. And I think OpenAI is really good at marketing. So they dropped ChatGPT right in the middle of NeurIPS. So there were two back-to-back AI conferences, right? NeurIPS at New Orleans, and then EMLP at Abu Dhabi. I was at both of them. So they dropped ChatGPT right in the middle of Europe, and all of a sudden, our top researcher, AI researcher at the conference, is talking about ChatGPT, right? So it quickly spread both in person and on Twitter, right? And then every paper being presented there, especially at EMLP, the authors got to answer the question, hey, what does ChatGPT mean for your research? And is this still relevant, right? That's a kind of funny moment. And then language models can also like write code. And I think it is said that these days, like the code that is being written at Google, like more than 10% of all those codes is now being generated by some AI language model. So that's huge. And then also there are these multimodal language models as well for vision and audio. Okay? So all of these seem to point us towards a very appealing future where like natural language just serves as a universal device, right? Powered by language models for all kinds of automated problem solving and for interacting with the entire computing world, which if true will be truly like revolutionizing for our society. However, as we just discussed a little bit in the panel, there are still a lot of things missing in the current language models. And what I'm particularly interested in is well captured in these tweets I posted a couple of days after the ChatGPT release. I think there are a couple of like for example, like these two examples point to like two fundamental limitations of ChatGPT right now. One is that it cannot take actions. Well, for a lot of the things we want to do, it involves like taking actions, all kinds of actions in some kind of environment. But ChatGPT cannot take actions in any real world environment, right? And also, while ChatGPT is really good at some generic tasks or processing some generic knowledge, when it really comes down to some specific knowledge, some specific environment, it quickly falls short for doing a satisfactory job. So if I need some particular information that is not like at the head of the distribution on the internet, right? ChatGPT may have a hard time answering that. So that's what motivates grounded language understanding. Like grounding these language models to real world environments is what we will talk about today. So that includes, for example, things like Alexa or Siri, where it's really about taking actions in the real world, right? So they are backed by a bunch of APIs. You use the language to describe your needs, and that are translated into various APIs to do various kind of things, and then either get the information back to you or produce some state changing effects in the world. Or it could be like about some specific environments. Like, for example, if I work in a healthcare company, I don't care if like the language model knows that Biden is the current president of the United States or whether it knows Trump's birthday. All I care about is whether it understands my specific problem and my specific environment, right? And also a very appealing future is the combination of these language models and robots or embodied agents in general, where like the language model serves as like more like the brain, and the embodied agent serves as like the hands, the eyes, and the legs for the language model. So then the combination of the two will really deliver some game-changing applications. Okay, so here's one formal definition I will try to give for grounded language understanding. This is a heavily loaded term, so there certainly are different definitions, but here's the definition we will go with today. Okay, so given a natural language audience U and the target environment E, what we're trying to learn is a policy pi that takes U and E as input and generates a plan or a program P. So we will use plan and program interchangeably. And such that the denotation of U in the environment E is the same as the denotation of the plan P in the same environment. Okay, so that might be a bit abstract, but actually it's very easy to understand. So let's say we are dealing with a database. The user may want to find something in the database. It's a private database. The user just says something in her own words. So that's U. And then we map that, the model, language model maps that into a SQL query, which is P. And when executed, the denotation of P in this database E will achieve the desired effect of the utterance U, right? So we are taking, by taking this definition, we are taking like a model-centric semantics view here, which is a very natural for a natural fit for grounded language understanding. Okay, so when we are on board with this definition, then we can start talking about the challenges, the unique challenges associated with this problem compared with other general NLP problems. A very interesting challenge is that there is just an infinite number of different environments. Like just take databases as an example, right? So literally every company has their own, and every organization has their own database. So there's like millions of databases out there. And also one environment could have an infinite number of different states. Like for example, for a physical world, like for a teaching environment, right? The different states could be like different objects in that environment, or different positioning of these same objects, and so on and so forth. So that brings another dimension of a variation here. And also this environment states could be dynamic, right? So like, for example, the database may be like constantly changing. So all of these things together just makes this recipe for language models that we're used to. Like you get like just a large corpus of things like text, and then you just pre-train a model on it so that it will just become better for everything else. That recipe doesn't work that well in principle because of these like unique properties of this problem. So just take some more examples. If the environment is a knowledge base, then we may have an utterance like this. And then this environment is associated with a certain formal language. Here we have a Lisp-like formal language here. So the syntax should be easy to recognize that can represent the utterances like this in these particular environments. And then if we have a physical world, and imagine we have a robot that can follow these language instructions to do this task in a physical world, then the plan could be something quite different, right? So to make a cup of coffee, then the first action is probably to find a cup, right? And then in that particular environment, depending on the position and the pose of the agent and the position of the cup, then the agent may need to take a different sequence of actions in order to achieve the same effect. So you can see there's a strong dependency on the environment here. Okay, and fundamentally, a challenge here is really the classic symbol grounding problem, right? So we have the same meaning represented in different languages, right? We have our daily natural language, and which is what language models are trained on. And then what we need are these plans and programs expressed in different environments and different formal languages associated with those environments to express the same thing. So how to ground one to another is really the challenge here. Okay, so hopefully that sets the stage. So now I'll talk about two recent work from my group, just to give you a taste about what are some possible modeling approaches to tackle this problem. The first work is done by my PhD student Yu and another PhD student Xiangden from OSU, working with Professor Huan San, and it's called PanGu, and where we try to come up with a unified framework for grounded language understanding. Okay, so before delving into the details, let's take a quick quiz. The first question. So here we want to find the right program corresponding to this natural language question over a knowledge base. And I won't tell you what this formal language is, what's the semantics and syntax and so on and so forth. But just looking at these candidate programs, can someone tell me what would be the right answer to this question? Maybe just type in the chat.
I want to ask ChatGPT for this, to be honest.
ChatGPT can certainly do this if you formulate the problem in this way. Any guess from the audience? A, B, C? Okay. Bingo, we got a guess. And okay, we got another one. Right, so actually B is the correct answer. Thank you, Bao-Ming. Well, we can sort of get various kind of clues by just comparing the question with the programs, right? So, okay, so we are looking for some coach and some hockey coach in particular. So this one is talking about some cricket coach, so probably not the right answer. And this one is talking about some hockey team, maybe a good answer. But then if we compare these two, then this one doesn't talk about coach at all. So then probably the answer is B, right? So without even knowing the syntax or semantics of these formal languages, we can take an educated guess at this problem for most people. But how about this, a different flavor of this problem? Now you're just given the natural language question, and you're asked to write the corresponding program from scratch. Well, I won't ask you to do it because it will be too hard. Because the programs will look like this. The details don't matter here, but you can see the difference in difficulty. The second question is apparently much more difficult than the first one. The reason is that, well, to do the second question, you need to learn the grammar of this formal language, which is a specific kind of Lisp language that we didn't introduce the grammar. And then you also need to know the environmental specifics. Like, for example, you need to know, okay, in this particular knowledge base, M10 engine is represented as this string M10, and this classification relation sort of maps to a engine type used in relation. Well, so you need to know all these things before you can write down the correct program. Okay. And in reality, some of these environments could be extremely complex. Like in the knowledge base that we will use later, it contains like 40 million entities, 3 billion facts, and thousands of relations and the entity types. So these are massive environments, and you need to know all these specifics in order to write down the correct program, which is obviously very hard. And that's the same thing for language models, right? So it's also hard for language models to write these correct programs from based on the utterance. So the key challenge, the key message, takeaway message I hope to make through this talk is that generation, for grounded language understanding, generation might not be the way to go. And discrimination using language models may be a better choice. Okay, because to make it more explicit, directly generating plans or programs in an autoregressive way may not be the optimal way of using language models for grounded language understanding. That leads us to Pangu, which is a unified framework that models grounded language understanding as a discrimination task. Okay, so before talking about the technical details, let's take a quick look at what current methods approach this problem. Well, most current approach would just take the autoregressive generation route. Just use a sequence-to-sequence language model. So encodes the input utterance and then generates the plan token by token, right? So we have these things like this for text-to-SQL parsing. I have similar things for question answering over knowledge bases that use just a T5 model to generate the plan. And then even for embodied AI for these robots, we are doing the same thing. So you have like the utterance from user, and then you try to generate, produce a plan for the agent in an autoregressive fashion. Okay. However, such autoregressive generation can produce invalid plans. Here are two studies that showed some statistics about that. So for this work for embodied AI, we find that people find that a large number of the generated plans by these larger language models are not valid. So they either have grammatical errors, or they are grammatical, but when executing them for various reasons, they would lead to execution errors. And then similarly for KBQA, if we just use a language model to generate the plans, then we would also see a lot of invalid plans. So in a kind of intuitive fix to these problems that I bet many people are already thinking right now is maybe you can just, if there are such constraints like to be grammatical and to be faithful to the environments, then maybe we'll just model these as constraints. So we just do constraint decoding, right? So here we're showing a beam search process. And then you may have like some, for example, some grammatical constraints. Like the first token must be a left parenthesis, and then it must be followed by some function name and so on and so forth. So you bake these constraints, you write down these constraints, bake these constraints into the beam search process, and then you just kick off whenever you run into a hypothesis that doesn't conform to any constraints, then you just kick it off the beam to guide. In this way, you guide your beam search process, right? So fairly standard constraint decoding. But we will see that these may not be ideal as well. So one particular salient problem with constraint decoding is that it can be hard to control, and oftentimes it can be short-sighted because constraint decoding is really just doing local normalization, but we won't get into details like this. We'll just show a quick example. So consider this example, and we're generating this program token by token in a left to right fashion. And let's say we have some constraint decoding, but for various reasons, when we're decoding at this step, maybe because bias in the training data, maybe just because various other reasons, like the model thinks that this join function is more plausible than the ground truth AND function, possibly because it's also followed by a keyword sound. And then only after many decoding steps, when the model starts to decode this recording keyword, then it may realize that, okay, now this program may not be very compatible with the input utterance. But when the model is decoding this token, it's very hard to tell. And when we're at here, it's already too late to correct this error, right? So this is what would mean that these kind of autoregressive generation could often be short-sighted. Okay, now let's take a look at the proposed Pangu framework, right? So in this framework, we have two things. We have a symbolic agent that will search the environments, whatever environment that is, to propose valid candidate plans. So these plans are guaranteed by design to be grammatical, to be faithful to the environment, and it's very easy to control the search process of the symbolic agents. And then the neural language model is only used to score these plans. So which candidate plan is better, right? So that's exactly what we were doing in our quiz earlier, the first question in the quiz, right? So the language model is only asked to compare like which one is more plausible, right? And then these scores provided by the language model will then be used to guide the search process of the agents in the environments, okay? So by this separation of this neural world and the symbolic world, we allow the language model to focus on discrimination, which turns out to be a much easier task. We give some intuition about that in the example earlier. And then this framework is also generic for many different kinds of grounded language understanding tasks, because we make very little assumptions. Okay, I think I need to speed up a little bit.
Sorry, yeah, maybe you have like 5 or 6 minutes. Thank you.
Yep.
Sorry.
So I'll skip some technical details. So let's just take a quick look at the Pangu framework. At a high level, it's really, really simple. So it's the core thing is just 3 lines here in the algorithm. So you start with some initial plans, P0, and then at each iteration, you will generate some candidate plans based on your current plans and based on the environment. So you get a candidate set CT, and then you use a language model to score these candidate plans to get the top K. So it's like a beam search type of process. Then you get PT, and then you just do a termination check. And if that check passes, then you just return the top scored plan, right? So at a conceptual level, this is extremely simple. Now, let's take a look at a concrete example. I think that's sufficient for understanding the gist of this approach. So we will use KBQA as a test bed. And as I mentioned before, these knowledge bases are extremely massive, right? So there's very little environment that can go more complex than this. So it provides an ideal test bed, right? So we have to start with this question, then the agent will detect some initial plans, which is really just doing entity linking in this case, and find the entity Java in the knowledge base. And then it proposed some candidate plans based on this initial plan, just the one hop valid plans from this entity. And then use a language model to score them. And let's say if we do bin search with bin size 1, then we keep the top K. Then we execute this plan, gets to a new state, and then generate some new, more complex plans, and then score them again until we pass the termination check. So until like the termination check determines that, okay, this plan is good enough for this orderance, and then we stop the search process. Okay, now let me quickly show some results. So it turns out Pangu is a very effective framework. Like just simply using a BERT-based model as the language model, it can already set a new state of the art on most standard KVQA datasets. Like this is on Grail QA, this is on graph questions, and this is on web questions. And then also it gives a very reliable gain over model size. So if you just use a larger language model, then it will give you a very reliable gain. And it also allows for like a very an unprecedented level of flexibility of using language models. So you can use these BERTs, like these encoder-only language models. You can use T5, these encoder-decoder language models. And I'll also show that you can also use large language models like Codex, these decoder-only models, and that and you can do in-context learning with it. So using Codex, like just use 10 training examples with Codex. It's already showing very strong performance. And I should note that this is the very first time anyone managed to use in-context learning with large language models for KVQA. So this is just some remarkable results, I would say. We also show that Pangu, because discrimination turned out to be so much easier to learn than generation, so Pangu significantly improved sample efficiency as well, but we will skip this. This is talking about why Pangu is better than constraint decoding, but we will skip this. So I had a second part where we will talk about how to use large language models for embodied AI, but I think I'll probably just skip this part, most of it as well, but you can just quickly see the slides. And I'll just use 30 seconds to talk about the gist of the approach. So for embodied AI, as we talked about earlier, there's a very strong dependency on the environment. So if you just ask the language model to directly generate this highly environment dependent plan, it won't work. So what we did here is we do hierarchical planning. So we have a high level plan and a lower level plan. And the large language model only needs to do high level plan, which in a sense is more or less common sense reasoning. So make me a cup of coffee always involves like get to a cup, pick up a cup, get to a coffee machine, and so on and so forth. So that makes it possible for a language model to do planning for embodied agents. And then we also have some dynamic grounded planning. So when we use the environmental perception to dynamically adjust the plans to make the plans more grounded. I'll skip the demo. Yeah, and the results are extremely good as well. So just using 100 examples, we're also getting comparable results with existing methods that use like 200 times more training data. Okay, so in terms of future work, I think there are a lot of interesting, I think we're really just taking baby steps in this space, and there is a ton of interesting things to try next, and we very welcome like collaborations in this space. With that, I'll conclude the talk. Thank you.
Thank you. This is really amazing. I think I'm not sure if we have questions so far, but I didn't see any question popping up. Yeah, so I think since our next speaker is ready, I'm sorry to interrupt you, Professor, but this is really nice. Thank you so much.
No problem at all. Yeah, and feel free to shoot me an email if you're interested in anything or questions.
Yeah, thank you so much.
Thanks for having me.
Thank you. Yeah, so let's quickly move on to the last session. So this session, including 4 speakers, they will talk about general machine learning applications and technologies. So let's first welcome Yujie Qiao. She is a master's student at Yale University. So yeah, please go ahead, Yujie.
Thanks, Irene. Okay, I'll share my screen.
Yeah, we can see.
Okay, great, perfect. Okay, hi everyone. My name is Yujie. Today I'll be talking about natural language processing for neuroscience database mining. So this is a joint work with Dr. Robert McDougall at Yale School of Public Health and Evan Kudan, who is a computational biology PhD student at Yale. So before we start, I want to give a brief intro about the 2 terms that will reoccur throughout my talk today. So the first term is online neuroinformatics databases. As we know, the process of studying brains generates massive amount of data, and neuroscience researchers often publish papers with an emphasis on data structure and software tools related to their analysis. And they often came with computational simulations of models. So in order to better organize and share those complex experimental data, neuroinformatics databases are created so that data uploaded by neuroscientists will be aggregated to facilitate discovering novel neuroscience experiments. So the second term I'm going to mention today is metadata. As many of you probably have known, metadata is like a more granular level of data, which describes the original data. That is very important for navigating the relationship across data at all levels. Okay, so why do we care? So the basic motivation behind this project is that we saw the attention of machine learning community to neuroinformatics remains relatively limited compared to applications such as NLP and computer vision. Although there are still like many benefits we can get from applying machine learning to neuroinformatics. And we think this happened because of the following reasons. So first of all, there were many high quality computational neuroscience data sets out there, which prevents researchers from doing machine learning problems. And the second thing is existing data sets. They're also very, very messy, and they're in many different data types, including experimental readouts, curated annotations, and metadata. So this created an immense amount of challenges for human or machine learning algorithms to learn how to assign metadata tags properly. And the third reason is that with this high amount of explosive amount of disparate data, it takes lifetime for non-domain experts to curate data sets of interest. And they often require users to possess some kind of like disciplinary expertise. So what will be our solutions to those challenges? So in this project, we propose to start with a very simple task, which is making predictions of metadata tags in one of the largest computational neuroscience database called ModelDB. So we implemented 2 language models and combined with machine learning algorithm to help us automatically predict metadata tags. So this tool will have the potential to help neuroscience informatics researchers process the increasing amount of data generated by individual labs and large neuroscience initiatives. And further, this prediction tool can potentially help us discover patterns in metadata, and potentially we can benefit the broad neuroscience community. So let's move on to the core topic for today, which is ModelDB. And speaking of ModelDB, I would like to first give a tribute to its creator, Dr. Gordon Shepherd, who is an American neuroscientist and professor of neuroscience at Yale School of Medicine. He was the first person to introduce olfactory system as an accessible model for study of the functional organization of a forebrain cortical structure in the 50s. He also pioneered the study of neurogastronomy and neuroanalogy, connecting our sense of smell and activity in our brain with our experience of both food and wine. He founded Sense Lab in 1993 as part of the original Human Brain Project, where he began the development of neuroinformatics tools in support of neuroscience research. And about 3 years later, ModelDB was created as part of the Sense Lab project by Dr. Shepherd and a group of Yale researchers. So let's talk about a little bit more background about ModelDB. So ModelDB is a computational neuroscience repository with a source code of over 1,700 published neuroscience models in their original source code form. Models are associated with metadata tags such as brain region, cell types, channels, receptors. So here, as I display here, is an example of a computational model and its homepage. As you can see here, the model has actually three tabs. So the first two tabs included the model information and source code. In addition, there is a third tab called citation, which has cross-referencing with keywords and related literature to identify relevant related work. As I will explain later, this tab encompasses the key information and would be the emphasis of our project here, because they are in a nice and clean textual format, which is ideal for us to do text mining. So here is like a typical display of what a user will navigate when they go onto the ModelDB page. So if a user wants to submit a new model, you kind of need to input your full name, email address, just like some basic contact information. And after you confirm, you paste your abstract of the paper you are going to submit, and there will be a new dialog pop out from the window. And then the system will automatically give you some suggested results. For example, here we can see synapses, prefrontal cortex, and realistic network. So as a user, you can choose to accept or reject those suggestions. And finally, is there just like some extra metadata tags you can choose for submission of your model. So as you can probably see here, this process is very, very human curation heavy, and it requires a lot of time. So that's motivated us to automate this process. So that was about ModelDB, but how do we come up with the right language models for our tasks here? Well, as I previously mentioned, ModelDB has cross-referencing with keywords and related literature. So it would be ideal for us to find a language model that has a powerful signal of document level relatedness. And luckily, in 2020, the researchers at the Allen Institute came up with a new language model by the name Spectre. So Spectre was developed specifically for generating document level embedding of scientific documents based on pre-training a transformer language model on a powerful signal of document level relatedness. It uses Cybert as foundation and then trains the model on a large corpus of citations to output representations that are more similar to papers that share citation links than those that do not. It builds embeddings from the titles and abstracts of a paper. And the second language model we're considering here is called LinkBird. And this is actually developed by Michi, who was also a one of the panelists here. So LinkBird, similar to Spectre, is a language model pre-training method that leverages links between documents, specifically for citation links. So given a text corpus, this model view as a graph of documents and create a language model's inputs by placing linked documents in the same context. It also has a biomedical domain curated submodel called BioLinkBird. So we choose BioLinkBird base as our model here because it was pre-trained on PubMed abstracts for document relationship. So I think that would be more suitable for our task here. And also we chose LinkBird because of its better performance of performing cross-document tasks, where features such as citation links, including knowledge that spans across multiple documents, can be largely captured in this model. So for our corpus here, we gather plain text versions of all the titles and abstracts of the 1,568 published papers as of April 29, 2022 in ModelDB. And for a paper that has not, that without abstract, so an expert of the first page was used instead. So the unit of data in ModelDB is a model, but since model are typically not formally published themselves, all metadata prediction was done based on the text of an associated publication. So I'll talk more about our experiments here. So first of all, we did data preprocessing and we created the embeddings. So for preprocessing the abstract text, we first linked each model ID with its cited multiple model paper IDs in order to map the M to N relationships. We then took each model paper ID and its corresponding PubMed ID in order to get its titles and abstracts. And we also implemented a parser to return a data structure. The preprocessed data were stored in a JSON format. And next, ideally, we will run classification accuracy tests for all of the available tags. However, consider the fact that tags with extreme high or low frequency would not yield consistent prediction results. So we remove them from our analysis. And after filtering out the tags with frequency below 3 times or above 115 times, we did additional cleaning of the metadata tags. So for the case where a metadata tag has a corresponding tag called web link to model, we return the tag's ID without a corresponding tag. So for example, the neural Visio here, we return the one without the tag web link to model. And second, we remove duplicated tags, such as consolidating the tags Brian to Brian. And lastly, we remove tags such as Allen Institute because of their reputational biases. So as the after the filtering results, there were only about like 450 tags remaining for our analysis. As a last step, we use the pre-trained Spectre model to embed the preprocessed data. We ran inference on the provided input and write the embedded document and its Spectre representation to a persistent dictionary for faster access later. So here I'll walk through a basic example of how we go from a raw data text to generate the embedding representation for each model. So here is a JSON format of each computational model. So as we can see here, for example, we're trying to predict Parkinson's as one of the metadata tags. And we can see here for each model, it has a model paper. So what we did here is we retrieved the PubMed IDs of the paper each model paper sites, and we extracted the abstracts of those cited papers as shown. I will show you in the next slide. So similar intuition as LinkBird, the reason that we want to generate such similar representation is that if we're able to, generate, put similar papers that has similar representation together, we will be able to, predict the unit's metadata tag based on the other unit's metadata tags. But here, there's like a key assumption we need to have, which is we need to assume that the golden labeled metadata tag has consistency across all units, which means that the metadata tag need to represent the true topics of each unit. Here is just like a more further step of how we fit the combined text, which is abstract and title, into the spectrum model for generating 768 dimension matrices. And the last three steps of our experiments is, so first we tested LinkBird as an alternative model for embedding. So which is similar process as what we did for Spectre. And specifically, as I mentioned earlier, we use BioLinkBird based model, which was pre-trained on PubMed abstracts. So which we believe will yield better results because our text here is mostly biomedical domain text. And next, we use different strategies to embed the preprocessed data. First, we use SciSpaCy to preprocess the abstract text. And we then combine SciSpaCy with max and average polling strategies for creating 100 and 1568 and 400 matrices. And for each PubMed ID, we also tested the 200, 600, and 800 dimensions, just to make sure the 400 dimensions would be the ideal level of dimensions. And lastly, we combine such representation and put them into the classifier. So we did a bunch of tests, including Gaussian naive Bayes, and also support vector machine and k-nearest neighbor and logistic regression. And we also use leave one out cross validation for evaluating the model. Yeah, so these are all the classifiers that we test because we believe they perform very well on classification tests, and it has a very great generalizability. And for evaluation, we simply just use the F1 measure to generate the F1 score for all the classification results. Oops, sorry. So after carrying out the experiments, so first of all, we found that across the 4 classifier, it seems like Gaussian naive Bayes is the best classifier out there because as we've shown here, here are the confusion matrices of all the different classifiers. So the F1 score for GMB is about 0.76, and the F1 score for support vector machine is about 0.75. And also I need to mention that all of the classification results was done under the same embedding method for fair comparisons. So yeah, next I will show you the results for logistic regression and k-nearest neighbor. And compared to the previous, we found that GMB is the best classifier. So as a result, we restricted our further analysis and we use GMB as our only classifier. Next, we selected a few metadata tags and compared their prediction accuracy from alternative embedding strategies to the Spectre embedding method. So as shown in this table here, Spectre method outperform all the other strategies in general for most metadata tags. And the BioLinkBird method ranked in the 2nd place. So for example, as you can see here, for the tag Parkinson's, Spectre has a F1 score as high as 0.76, while the other three methods can barely surpass 0.50. And for other tags, for example, edge current, CA1 pyramidal cell, and hippocampus, Spectre was the top performer across all the methods. The only case where Spectre was not very good is the last one, which is like a name of the researcher. Here, BioLinkBird has the best performance across all of the methods. So further, we restricted our analysis to compare Spectre versus LinkBird on their embedding abilities. So we first selected the tags where F1 scores under the LinkBird method is above 0.20. And we showed their corresponding F1 scores under Spectre. So as you can see from the figure here, we observed that Spectre outperformed LinkBird in most cases, with only 9 exceptions out of the 45 example tags presented here. In this plot, the blue dots represent the performance for Spectre, and the green ones LinkBird. And you can see there's like some tags, there's like a huge performance gaps between the two methods. In addition, we selected the tags where F1 scores reached 0.13 and above, but below 0.20 under the LinkBird method. And we show their corresponding F1 scores with Spectre as well. So similarly, Spectre still outperformed LinkBird in a majority of tags, with only 8 exceptions out of the 55 example tags, which fell under this scenario. Next, we ran classification accuracy tests for all available tags under the Spectre embedding method. And not out of surprise, out of 451 tags, 35 tags achieved F1 score of greater or equal to 0.50. And in particular, the F1 scores of pituitary cell reached F1 score as high as 0.95, which is kind of pretty impressive. So this followed by Gray cell, which has score of 0.79, and olfaction, which has a score of 0.77. So what does this result mean? After generating all of the data, and we did a further analysis, and we came up with some pattern observations and the associated biological interpretation. So the first salient pattern that we observed is that among the metadata tags which achieve the higher F1 score, first, terms that are very specific, such as pituitary cell or nitric oxide, which is a type of neurotransmitter, are often used by neuroscience researchers in their publications, usually in their titles or abstracts. And another example where the terms were very specific were tags such as heart disease or like heart cell. A trivial knowledge is that neuroscience researchers sometimes they study the ion channels in the muscle cells in order to model the electricity of neurons. So that's why they coded heart disease and heart cells and put them into their titles or abstracts, because it is very noticeable or very unique for their publication. But on the opposite, some general terms such as common ion channels, such as potassium or calcium, were very much less likely to be mentioned in the titles or abstracts unless the papers were specifically studying those ion channels. And second, even neuroscience researchers has a very consistent writing style, it will be very easy to predict the metadata tag associated with that author. This was exactly the case. So we found that so there's a researcher, his name is Tim Masquelier, who was an MIT affiliated researcher. So we hop onto the database and we checked all of the computational models uploaded by this researcher. And we found that in every single model uploaded by him, there was a term called STDP, which is a type of learning. So that is, I think that kind of explains why it is very not surprising to predict these researchers' work associated tags in every of our tests. But on the other hand, tags associated with researchers, such as some other names, achieve a very low F1 score. So we conjecture this happened because they cover those researchers. They cover a much wider range of topics in their research. And the third pattern that we observed that is there was a significant amount of metadata tags which has like invalid F1 scores, meaning they were basically unable to be predicted. So we conjecture this happened because of the following reasons. So first of all, terms that are very general, which can be used in a wide range of topics, are kind of impossible to capture their patterns of occurrence. And next, terms that are either too specific or largely understudied, and so that like very few researchers are using them for their study. They were also very hard to predict. So examples for this under this scenario are tags, for example, Brian 2 and Kiwi 4.3, KCND3. So these are like very unusual tags, which is like very hard to predict. And lastly, there's like a pattern that we observe that there are many neurons of which the names are not very standardized. So for example, hippocampus CA1 PV plus fast firing interneuron lacks kind of like standardized names. But in comparison, hippocampus CA1 pyramidal would be very easy to predict because everyone in the neuroscience community would assume and agrees on the same name based on the higher intensity of study of this name. So in conclusion, what we did here is that we presented a new metadata tags predictor for the neuroscience database called ModelDB. We achieved this by testing two language models, LinkBird and Spectre, on their ability to map the inter-document relatedness from titles and abstracts. And we then combined the resulting embedded representation with a Gaussian naive-based classifier to predict metadata tags with the hopes that we can inform greater biological interpretations, and which can be further benefit the neuroscience community. And different than previously developed rule-based methods, our work demonstrated that there's like a new direction for metadata tag predictor by using machine learning and NLP techniques. I guess the most important takeaways here is that machine learning can enable human to efficiently identify metadata tag tagging patterns, which is the new direction, I guess, for online neuroscience database mining. And some of the future directions I would propose is that, so first, maybe we can try use LinkBird as a drop-in replacement for Spectre. And next, we can text deep neural network as additional classifier. And third, we can improve the data quality of the metadata tags. And lastly, as I listened to the interesting panel discussion today, maybe we can test ChatGPT or GPT-3 with regard to their ability to generate this new embedding representation, and we can implement with prompt engineering, for example, champ thought, and we can compare them with the current method. And with that, I would like to conclude my talk, and I would like to thank Michi and my advisor Drago and Professor Aman Cohen for their brilliant ideas for contributing to the experimental design. And yeah, that's my talk today. Thank you all for listening.
Thank you so much, Yijie. I'm sorry, I do think that we may only have time for one really quick question. Let's see if the audience have any question for that. Actually, I'm pretty interested in the, like one of your conclusion was that you were saying that like certain approach, which is based on machine learning and maybe potentially NLP techniques are better than rule-based systems. I think this is pretty interesting because based on our experiences, like so far we did everything, almost like most of the tasks we did for medical text, the rule-based system is is actually dominating the field. It's really hard to see like deep learning based research can surpass the traditional rule-based method.
Yeah, I think that's a very interesting observation. And actually, so my advisor, Dr. Robert McDougall, he actually published a paper before, which is, like the same mining on the same database, PhotoDB, and he was using the rule-based method. But I think, like as I mentioned, the reason that we want to implement this new kind of like a new direction is that we saw the opportunity of the current state of art language model, which is vector and link-BERT. They can just capture the powerful signal of interdocument relatedness, which is something all the previous natural language models cannot capture before. So we were very lucky to have those language model, and we combine with machine learning, and we can generate like better performance. Yeah, so I think the most exciting part of this work is that different from previously rule-based, now we're able to pursue another possible avenue for this type of textual database mining.
Yeah, exactly. Okay, yeah, thank you so much, Yijie, again for this amazing talk. Let's just move to our next speaker. Thank you. Our next speaker is Lauren Gillespie from Stanford University. So Lauren, if you can go ahead and share your screen to start.
Okay, I'll work on that right now.
Yes, we can see it.
Wonderful. Let's see if I can get the bar out of the way. Cool. Awesome. Yeah, so like Irene said, my name is Lauren. I'm a fourth-year computer science PhD at Stanford, and I've been working on how we can use machine learning and open science to predict plant biodiversity at scale. So with that, see if my slides will advance. Awesome. So hopefully I don't have to convince any of y'all that plant biodiversity worldwide is in peril, mainly due to human-driven land use and climate change. And this is a worldwide decreasing native plant biodiversity from Brazil to the US to Eastern Asia, Europe, and beyond. This local loss of plant species biodiversity is very important because it negatively affects many ecosystem services important for human life, such as carbon sequestration, primary productivity, so how much carbon plants store, local climate regulation as well, and then just overall ecosystem resilience to increasingly common extreme weather events, such as fire, which is pretty common here in California. However, plants move very slowly as a species across space and time, since individual plants themselves can't actually move during their lifetime. They're fixed in place by the root system. That being said, even though plants move very slowly, the speed of climate change itself on plants has been accelerating over time, meaning that resolution becomes super critical when we're thinking about how to track the effects of climate change on plant species worldwide. And therefore, the higher the resolution of the sorts of predictions we can make about plant species biodiversity, the better we can react and more effectively plan for a rapidly changing climate future, such as here in California, where severe wildfire is a large threat. If we could say, for example, generate a rapid assessment of what plant species we think might have been lost after a blaze, that could be really helpful for thinking about ways that we could help the forest recover from that fire. That being said, collecting this kind of data that we would need to do this sort of plant biodiversity monitoring and to make those high resolution maps I just talked about is actually extremely difficult. As you can imagine, it's pretty time consuming and expensive to run traditional on the ground surveys where you have somebody going around with a just like looking for species essentially out in the woods. And even in California, where there's a very large environmental budget and a lot of volunteers that try to work on these kinds of questions, still in the state, we've only managed to map half of the vegetation of California in over a decade-long effort to do so at scale. And so really traditional survey methods are just not quite cutting it when it comes to doing the kind of rapid assessment that we'll need as the climate changes faster and faster. So alternative methods besides sending someone out in the field with a clipboard to look for plants do exist, specifically in the form of what we call a species distribution model. So species distribution model is essentially a term for correlating known occurrence records of the species. So, you know, you might have a few hundred observations for a pine tree of interest of yours. And what you can do is you can take some sort of environmental variable that you think might be important for how that tree, where that tree can live essentially. So like maybe it's temperature, or precipitation, or something else that drives plant growth. I mean, you can essentially correlate these important environmental variables with the known occurrences that you have of this species, and then essentially interpolate across a given geographic area to where you think a species is present based on the underlying climate variables in the entire region. And so this is how you can get over actually having to go in the field and look for plants one by one, is by essentially inferring the full range of the species based on some variable of interest. As you can imagine, this method is a lot easier and less time intensive because you need a lot less data than, again, collecting individual plants all across the state. And it also takes relatively little time to generate. These algorithms usually take a few minutes to run tops. But unfortunately, much like with traditional surveying methods, the environmental variables actually used to fit these species distribution models tend to be very low resolution. They tend to be decadally average climate data. So if we take this example of a wetland that was restored in Northern California in 2013, between 2012 and 2014, you can see in the imagery how the middle of the watershed got a lot greener after the ponds were restored. However, if you actually look at the traditional data used to fit a species distribution model that say the wetland cattails that would live in these ponds, you're not going to be able to get that from this information because it's, again, been averaged across decades, and it's also been averaged in a large spatial resolution. And this is done to improve the fit of these models. Because again, when we're talking about only a few hundred to a few thousand observation, noise becomes really important. And so the way to maximize the predictability of your algorithm is to sort of smooth out variance and noise in your temperature and weather sampling, which you would get from using, say, the exact temperature like Tuesday at 5 p.m. versus averaged across, again, decades usually. So then this brings up the question that my research is interested in, is essentially how can we detect where plants are at high resolution, both in space and time, without running into these issues of resolution with the traditional data sources that species distribution modelers typically use. This is where the machine learning, really specifically deep learning side, comes in. So the first step to this process was that I put together a new multi-label biodiversity data set by taking observations, so essentially pictures of plants from across California, from this really cool app called iNaturalist that you might have heard of. Essentially, iNaturalist is this like community collaborative network where someone can take a picture of a plant and then get help IDing that plant. So if they want to like learn what species of plant they saw when they're out hiking, they can take a picture of it and upload it to iNaturalist. And if enough other people essentially agree that this picture you took is of a redwood, for example, then that observation will get uploaded to a publicly available database. So where scientists like me can essentially take the latitude and longitude of where that picture was taken and then use it for species distribution modeling. So in California, we have about 2 million observations from iNaturalist, but many of them don't reach the threshold of having at least 2 other reviewers agreeing on what species is present in the image. So if we filter to what are called research grade observations, and we only filter to species which have more than 1,000 observations in the state, That leaves us with a little over 650,000 observations of over 2,200 plant species across the entire state. We also turn into a multi-label data set by imputing any nearby species in a 256-meter radius, which I will explain why that's important in a little bit. We then pair each observation with essentially a 256 by 256 meter image taken from the National Aerial Imagery Program, which gives us a data set with over 650,000 image species pairs. We then take a classic ResNet-based feature extractor to extract 2D topographical information from the remote sensing imagery. And then we also use just a simple multi-layered perceptron as well to include climate data. But since both of those have very different resolutions, as I showed you earlier, it requires ensembling across architecture, as you can see here. We also predict the family and genus as well to help with species that don't have very big observations. So that being said, using a data set that is taken from human pictures and whatever someone sees while they're out hiking contains many biases. The first bias is that many images only have 1 or 2 species nearby, while very few images actually have the number of species we would expect to be present in any 256-meter radius, which is around 200 to 400 species, depending on what habitat you're in. There's also this issue of that many species have very few observations, so only 200 or 300 or anywhere between 1,000 to 2,000, while there's a few species that have hundreds of thousands of observations. So you get a really long tail data set. So the way that we account for the first bias is that we use a novel loss function that essentially breaks down the contribution of species that are present in a given image to species that are not present. So in a classic ImageNet like scenario, you simply are taking the softmax log probability across across all the classes, like your 1,000 classes in ImageNet, and essentially interpreting as a probability distribution. In binary cross entropy, you're instead doing a joint probability distribution, which is what we do here. And then here with this loss function, we are considering for each image whether or not a species is present or absent as a different distribution, because again, species we know that are present, we have for the most part confirmed that they're present, and it's very rare that you'll see mislabels of species in this data set, but species that are not present are most likely could be potentially present, and someone just hasn't taken a picture of it and uploaded it to iNaturalist. So this scaling helps to essentially reweight the contribution of positive or present versus absent classes to the loss. For the second, we also really rely on the multi-label aspect of this data set and co-occurrence patterns, which have historically for ecology been very important for understanding species distribution. So if you happen to see this small herb next to this tree, and then you see the small herb again, chances are you're probably going to see the tree as well versus say a cactus or something else. So on to the results. So if we take deep biosphere and we compare it, which is the colloquial name we've been using for the deep neural network that I showed you earlier. If we compare this to standard species distribution models, which include maximum entropy or maxent, random forest, and then also a previous work that tried using a standard softmax cross entropy loss. We see that deep biosphere across a wide range of accuracy metrics outperforms all the other models. These metrics range all the way from object detection to species distribution modeling to binary accuracy. And across all of them, deep biosphere does the best, which is pretty cool. And it's cool that it has higher accuracy, but what does that actually mean for the usefulness of the model for say a vegetation ecologist or another biologist who is interested in trying to detect plants? And so one thing a good SDM should do is to be able to detect individual plants where we expect those plants to occur. So we can do that quite easily in California with redwoods. Redwoods, again, are a very charismatic tree that tends to grow, that only grows in California and then a little bit in Oregon. They're very, again, they're not endangered yet, but they are threatened by climate change as California gets drier and hotter and has more fires. The other problem is that in the 1900s, most of the redwoods in California were clear cut and logged completely to the ground. As you can see here in this image on the left, there's only a few places in California where old growth, as we call it, redwood forests still occur, which is those dark sort of bands in the right-hand side of the image. The rest being forests that were clear cut in the 70s and have since started to grow back. If we look at the official National Park Service vegetation map for this area, we can see that indeed the darker areas that we can visually see with our eyes correspond with the mature redwood grove vegetation class, versus the other areas typically are secondary redwood regrowth after that clear cutting. We can in fact ask a human to go and label where they think these old growth groves are present. But as you can see, humans are actually pretty poor at detecting where secondary growth is. They're only really good at detecting mature old growth redwoods, which is only about 5% of the redwoods left. Versus if we look at the predicted presence map of redwoods produced by deep biosphere, we can see that it, visually speaking, seems to both predict mature and secondary redwoods better than the humans did. If we compare to two of those baselines I showed you in the accuracy chart, we can see both of these models do not predict redwoods present in any pixel in the park, which we know is of course incorrect. So these models, of course, visually speaking, are just not going to be very useful for trying to find redwoods in California. And in fact, if we actually go and we look at if we compare the probabilities of pixels that have been labeled as redwoods versus those that have not been labeled as redwoods using that National Park Service map I showed you earlier, we can see that Deep Biosphere is the only model that predicts almost all of the pixels that have redwoods present as above 50%, which would be considered presence by most binary thresholds, and then predicts a lower probability for pixels that is not in the redwoods class. That being said, just because it's those other pixels can still have redwoods in them, they just may not be the most common species for the vegetation mapping that the national park did. So clearly this model is capturing important trends in redwood species distributions that the other versions, asking a human to find them, the Inception Net classic computer vision baseline, and then also the traditional species distribution model Maxent, neither can capture these trends well. What's really cool is we can also see that this model captures important trends in understory vegetation as well. Like, it's one thing for the model to be able to clearly see the visually visible redwood canopies. Now, what about co-occurrence interactions, like I mentioned earlier, or species you can't directly observe from satellite imagery? And that's where the multi-label aspect of this data set and the co-occurrence interactions I mentioned earlier come in. So if we take two not popular, but like well-studied understory herbs, so these are plants that grow under the large canopy of the redwoods. The first is boysenberry and the second is wood sorrel. Boysenberry, you tend to find it, according to national park surveys, more commonly growing in secondary redwood growth. So places that have been clear cut and then allowed to grow back after about 50 or so years, versus wood sorrel tends to be found in the older groves exclusively, the ones that have not yet been logged. So if we actually compare, essentially, if we take the difference in probability between the biosphere prediction of wood sorrel versus boysenberry, we can make this map here, where red means that the predicted probability of wood sorrel is higher than the predicted probability of boysenberry, and blue is vice versa. If we then go back and compare that to the official National Park Service vegetation map I showed you earlier, just with a different color scheme this time, we can see that again, that visually it does seem that the pattern we would expect, which with more boysenberries in blue areas and more redwood sorrel in red areas, visually it does appear to be occurring. We can of course then label each pixel based on using that national park vegetation map you see on the right. And what we do see is that for Oxalis oregana, which is redwood sorrel, that pixels that are marked as mature redwood groves tend to have a higher predicted probability than pixels not marked as mature redwood groves, and vice versa for secondary growth. You see the opposite relationship is true with boysenberry, which again matches our expectation about what species we should expect to see under the mature redwood canopy versus the secondary growth canopy, which is something that's important for conservationists who might potentially use this model one day, that the understory dynamics are properly captured, because oftentimes it's not the trees themselves may be at risk, but oftentimes the most endangered species are those growing under the small herbs that are hard to find. Beyond just individual species, we can actually use deep biosphere as well to capture more macro trends in ecology, such as spatial changes across landscapes. So looking here in Marin County in Northern California, what we can do is we can essentially take the average Euclidean distance between a pixel and its neighboring pixels to sort of get an idea of like how different are the species predicted in one pixel compared to all of its neighbors. The idea being that pixels that are more different than their neighbors might have a more unique set of species located there, or there's some other interesting biological properties that ecologists care about with this species turnover metric. And so we can actually map species turnover of it, using the predictions from our model and using this nearest neighbors averaging algorithm. We can then take the vegetation map of Marin County and essentially see, well, do pixels that have a higher predicted spatial community change, spatial turnover, they mean the same thing to biologists, depending on who you ask. Does there tend to be more, a larger different number of classes in a given pixel for a brighter or a higher spatial turnover than not? So you can see like there's this large olive green area in the middle that tends to have a low spatial turnover. And then there's areas where there's these woods interspersed with grasslands that has a lot of different vegetation classes very close to one another. And you can see that the predicted beta diversity is higher there. Now, as a sanity check, we can also look and see if you just take the same nearest neighbors average, but only for the raw pixels from the actual satellite imagery. Like maybe the model is just predicting, you know, where it's green and where it's not green. And we can actually confirm that by taking the same algorithm, but for the actual data used to train the model. And what we can see is that the biosphere's predictions have a much higher correlation with the number of vegetation classes from this map on the left-hand side per pixel, so those little boxes, than just using the raw NAIP data. So the model is not just predicting green, not green, and is actually indeed capturing, potentially, we likely think it's capturing actual differences in species composition across space. Again, something that ecologists care a lot about. The biosphere can also capture temporal changes in biodiversity as well. So if we take the example of the Rim Fire in Northern California, so the Rim Fire in 2013 was the second largest fire at the time in California's history and one of the most severe. If we look at this empirical metric of burn severity, we can see that indeed large swaths of Yosemite's forests were burned pretty badly during this fire. What we can do is essentially to try and estimate the temporal change in biodiversity in a given area, as we can essentially take the Euclidean distance of the predicted probabilities before and after, and essentially compare how much have the predicted species in a given pixel changed before versus after the fire, where the idea of more change implies bigger shift in the community, you know, something more severe, like a fire might have happened. So that's what you can see here on the bottom left is essentially this Euclidean distance metric using the biosphere's predicted probabilities from both 2012 and 2014, before versus after the fire. Again, we can do a sanity check of where we take the same distance, but using the raw NAIP data. So essentially the 4 channels are red, green, blue, infrared before versus the red, green, blue, infrared intensity after the fire, and take the difference of those 4 channels. And that's this map you can see here. And again, visually speaking, it does appear that the predicted change in community, temporal community change seems to be brighter where the fire is more severe according to the top right map than what you see in the bottom left map. And we can indeed corroborate this by correlating essentially per pixel the burn severity, the empirically and independently measured burn severity, to both the biosphere's temporal community change prediction and the raw Euclidean distance of the underlying satellite imagery. And we can see that again, the biosphere has a much, much stronger correlation. So the biosphere is much more likely to predict that a pixel or a given area saw more change in its species composition if it had if it was considered to be more severely burned than if you just did the same using the 4 bands from the satellite imagery, which is pretty cool. And again, matches expectations. The more severe fire, the less likely it is. It could be that the soil was sterilized, so the trees that were growing there before won't be able to grow there anymore because there's no seeds left to actually regenerate the forest, among other negative consequences. So it is expected that more severe burns means larger change in the community. In the last few minutes, I'll explain how not only can we use the biosphere to do individual species prediction changes, changes in both space and time, but we can also use it for a variety of other downstream tasks, such as vegetation mapping. So going back to the example of the redwoods I showed you earlier, this is Redwoods National Park in Northern California. And this is this is the, in order to generate the vegetation map I showed you earlier, the National Park Service went and sampled essentially what species are present in the like 400, roughly 1,000 points you see on the map here. What we can do is we can take those 1,000 points, we can take what vegetation type that the National Park Service determined was at each pixel, and then essentially take the final layer of our neural network and then use that as a feature extractor, fit random forest to predict the vegetation class. And what we see is that we actually see that on the held out set of field sites that was not used to fit random forest, that Deep Biosphere's features do a better job of predicting vegetation classes on unseen field sites than the actual official National Park Service map, which is pretty cool. So here's the vegetation map that Deep Biosphere predicted. And then here is the official map used by the National Park Service. And as you can see, there's around over 60% pixel agreement. And I only have a few minutes, only about 2 or 3 more minutes left. And this is, again, just showing you from that example we showed earlier of the redwoods. Finally, we can also use it for crop mapping, and I don't have too much time to get into it, but this is essentially showing Deep Biosphere does a better job of predicting crop type than state-of-the-art unsupervised learning approaches, which is pretty cool. And with that, I'm happy to take any questions.
Thank you, Lauren. Let's see if there are any questions from the audience. I think we do have time for 2 or 3 questions. At the same time, yeah, I'm just curious. So when you're doing the multi-label biomedical diversity prediction, is it like a flat structure because you have like so many different species, and then are they structuring in like a hierarchical structure or only a flat structure?
Yeah, that's a good question. Usually species will have, I had to go over it very briefly, but in terms of hierarchy, we of course have like species taxonomy, right? Like kingdom, order, family, genus, species. And we actually do use both family and genus level information as part of the predictions, but we kind of throw those away. We only use them during training to essentially help with species that might have very few observations, but have a very common other member of its genus and a bunch of predictions. So that's the way we try and encode the hierarchy. It's probably not the smartest way for us to do it, but it was what we tried first, and it seemed to help. But yeah, certainly there's, I think, a lot to be done with the actual taxonomy, because that encodes a lot of information about similarity of species, similarity of habitat, similarity of life cycles, among other things. So it is very important information.
Yeah, got it. Yeah, thanks for that. Let's see if there are more questions. So to the audience, you can type or you can just speak up. Yeah, I noticed that you have the like the images for, you see, either annotating or doing experiments directly on those images. So when you're taking those images, I'm not really sure if let's see, if the color, like what is the quality do you think the images are?
Yeah, so we didn't actually take the images ourselves. We actually got them from this nice program that the USDA runs called the National Aerial Imagery Program. And so they essentially have this whole process of taking high quality, high resolution photos of all of the continental US. The idea is so that the farmers can essentially monitor their crops across seasons. And they do a bunch of correcting to make the images more uniform. So they standardize all the images. They try and remove they also try and make sure that there's no clouds. So they'll like go multiple days to essentially make sure that there's not anything occluding the ground. And especially in California, where there's like not a lot of rain in the summer, you get essentially like 99-point-something% cloud free. But yeah, that's a good question. So thankfully they do all the data cleaning for the satellite imagery, and then I don't have to do it. But yes, it is very important.
Yeah. Okay, I think let's just stop here. Thank you again for showing this very amazing and interesting talk. Thanks.
Oh, thank you.
Yeah, okay, so now let's move to our third speaker in this session, whose name is Haoran Liu. She is a PhD student from Texas A&M University. So Haoran, if you can share your screen when you are ready. Yep, we can see your screen. Go ahead.
Great. So it's my great honor to be here, like to give a talk on my recent work, which is accepted by ICLR 23. And the topic is learning hierarchical protein representation via complete 3D graph networks. And a little introduction of myself. Like I'm a PhD student in computer science at Texas A&M University, and my advisor is Dr. James Cavali. And my research interest generally lies on deep learning on graphs, and I'm currently working on temporal graph neural networks and adversarial attacks on graphs. And previously, I worked with Dr. Shuiwang Ji, also from Texas A&M, on geometric deep learning for molecules. And for this part of direction, we have to work what is called ComNet, which is published at NeurIPS 22, and also this ProNet recently accepted by ICLR. And my email and my webpage is like listed on the right side. And just please feel free to contact me if you have any questions towards this talk, or if you want to discuss anything, I'm very happy to contact and discuss. So here's the outline of my today's talk. First, I will introduce the background on how to model proteins at 3D graphs, and also talk about the limitations of previous works. And also I will introduce how to design geometric representation with completeness, also efficiency, and also how can we model protein structure with complete 3D GNs. And also I will talk about the results and conclusion on our virus downstream tasks. Okay, so to start with, I want to introduce a little background on how to model molecules, like generally all kinds of molecules, like small molecules to very large molecules like proteins, as 3D graphs. So it's very natural that we can model a molecule as a graph, where we have atoms as nodes, and the edges are the bounds between the atoms. Then if we represent a molecule like a graph like this, we can just use some sort of GNNs, graph neural networks, and process to some message passing in the graph, and end up with node embeddings, node features, and we can put to a single representation vector, and then predict some properties of the molecule. So from previous works that we know that this work quite well. However, if we want to hear more about the structural properties of this molecule, for example, the energies or the forces of the very specific structure, and we need to make use of additional information, like 3D information of a molecule. And what I mean for the 3D information here is just the individual 3D coordinates of each item. So here with a 3D graph, we take the input of all the 3D coordinates of the atom, And so we can represent a molecule as like a 3D graph. And then we extract the 3D geometric representations from the graph, and we fed them into a 3D GN. And then we predict for the properties like energies or forces. Like, so at the branch down here is the mainly research branch across our current direction. So we also know that the protein structure learning is also very important. The structure of a protein generally determines its function. By understanding the structure of a protein, we can gain insight into how it functions and interacts with other molecules. Protein representation learning is very critical for understanding the behavior and interaction of proteins in our living systems. And it's also crucial for other research topics like drug discovery. So for example, if we have a protein function prediction that can help identify potential drug targets for the treatment of disease, that would be perfect. And it also can help us to understand the function of protein and can help researchers identify molecules that can bind into it and regulate its activity that is fall into this interaction part. Also, protein structure learning can help us understand disease mechanisms, as many diseases are caused by malfunctioning proteins. And also it works for agricultural and biotechnological applications, where protein plays a vital role in agriculture and biotechnologies. And also for basic research, protein function prediction is also very essential. It can help researchers understand the fundamental process of life, such as protein-protein interaction and signal transduction pathways. So we all know that the protein structure learning is very important. We really want to understand the protein function, like how it functions, by understanding the protein structure. However, learning from the protein structure is not a trivial problem, as so first we have its for a protein, we have amino acid sequence as the protein's primary structure, and then we know this amino acid sequence then fold together and fold into much complex secondary, tertiary, or even quaternary structures. Each of the protein is highly complex micromolecules that is consist of hundreds or even thousands of amino acids as a single unit. And also an amino acid is like, it's not a single node or it's not a single atom. It contains a detailed inner structure within each amino acid. To provide the motivation for our study, I would like to present some background information on amino acid and protein structure, which might be a very basic background that we just review, like the knowledge from our high school units. So there are 20 types of amino acids in nature, and basically amino acid is consists of a center carbon atom, amino group, and a carboxyl group, and a side chain. The difference among different amino acids lies on the side chain. Like the different side chain indicates the different type of amino acid. And all amino acids are linked together via peptide bonds, like like grouped together by the interaction between the amino group and carboxyl group of the next amino acid. And also for a protein structure that we can view it like on the top view, that we can view it, each amino acid as a single unit and link them together. And also if we look at closer, that we can like a finer gratitude, we can see the protein backbone, and which is consists of the nitrogen central carbon and carbon atom on each amino acid. And these 3 atoms on each amino acid link them together to form the full backbone for a whole protein. So for our study here, like we use some assumptions to on the protein structures to simplify and reduce the computation complexity of our model. So same to AlphaFold 2, we assume all bound angles and bound length are fully rigid. So for each protein structure, we treat each backbone structure as a rigid triangle, and also all the side chain structures as like the bound length and bound angles are fully rigid. So the remaining degree of freedom is are the torsion angles along the side chains of an amino acid. So the challenges of learning from 3D molecule structures is that first we have enantiomers, that it's kind of a pair of compounds with exactly the same connectivity, but opposite 3D dimension shapes. For example, the compound here, the penicillamine, is a chiral drug with the one chiral center and exists as a pair of enantiomers. The left hand side is a desired anti-arthrite, like a drug to help us with joints problems, and the compound on the right is extremely toxic. So for molecule property prediction, we have to be very careful that to distinguish these 2 structures, to have further design or for drug discovery, that to distinguish these chiral drugs that which might have very severe consequences in the following steps of drug discovery. And another example we need to distinguish all different structures here is the model, the molecule structures is really the energies or the forces, the properties we desire, is very sensitive to the rotation of a single bound. Like for example, here for this compound, we rotate one bound, and the energy alters dramatically with the rotation of this bound. So the question here is how to design geometric representation so we can capture all 3D information in molecule structures efficiently. So to this end, we propose our concept of completeness. So the definition of completeness is here, that for 2 3D graphs, and the designed geometric transformation for these 2 graphs is only identical when this 2 graph is identical, or say more intuitively, given a complete geometric representation, the relative position of nodes in a 3D graph can be uniquely determined. And also by using complete representation, the model can fully capture the geometric representation in a 3D graph. And it's also, the model is also able to distinguish any different 3D structures. For example, the examples we mentioned earlier, the chiral structures or bound rotations. So here we propose that the desired property for protein representation learning frameworks would be the hierarchical levels, that we want to consider different granularity, like for the proteins, like the all atom level, the amino acid or backbone, or all the atoms in a protein. And also we want the model to be complete, that we can fully capture all the 3D information within a structure. And our model should be able to distinguish all different, any two different 3D structures. And also, if just think of that the computation complexity by fulfilling the first two requirements would be very large, but we also wish our model to be very efficient, that we can train fast and inference fast. While all previous models are either not considering the hierarchical relations for proteins, or it's not complete. And also they might only consider one level of granularity. Our proposed model, ProNet, is able to consider all three hierarchical levels for proteins, and it is also complete at at each of these three levels. And also the computation complexity is of O and K, where the small n is the number of amino acids, and this is much smaller than the big N, which is the number of the atoms. Right. So here we will dive into the details of our proposed model, ProNet. And so the key research question here is, what 3D information should we use to capture protein structure completely? So for the first level, that assume that we only have the input of amino acids coordinates that we can view, like one amino acid as a node in this 3D graph. And we want to reach the completeness. We want to design a representation to reach the completeness of the structure. And by we achieve the completeness by using by considering the local and global completeness of the structure. I will introduce this in detail in the following slides. So how to achieve completeness for a simple 3D graph, that without the inner structure of the nodes, it's just a simple node. So we here proposed a local to global perspective. So for a local completeness, see here, we only consider one center node, I here, and consider it's all one-hop neighborhoods. And we want to build a local coordinate system for this node I, and so we can represent all the positions, or say relative positions, with all the neighbors within this local coordinate system, so that for this node I, all its neighbors' position will be uniquely determined within this local coordinate system, so that we can reach the completeness, the local completeness of this system. So for the local completeness, we first define the local coordinate system by using the node I and the first nearest neighbor Fi and Si at the second nearest neighbor. and we build a coordinate system on this. And then we can use spherical coordinates d, theta, and phi, like the distance angle between these two bounds and the dihera angle between the two planes to determine the relative position of each neighborhood node J. And also we want to combine two local systems together by using a rotation angle between these two nodes ij. And we further add a dihera angle between the plane with the first nearest neighbor of node I and first nearest neighbor of node J. And by using the bound rotation angle, we can link two local coordinate systems together and to further reach the global completeness system, global completeness of a system. So the complexity of this local and global completeness system is still ONK, just considering the d theta phi for local completeness and the further one torsion angle for global completeness. And so for the amino acid level, we can reach the completeness by considering these geometric informations. Then we need to consider further for backbone level, and the backbone level here where we take a closer look at the protein backbones, that we consider the rigid triangle for each amino acid. And so remember the assumptions we use for this, like we only need to model one more degree of freedom, that is the relation between any two rigid triangles within this system. So we use Euler angles to explicitly capture such information so that we can reach completeness at this backbone level. And also for the all atom level, and we still want to capture all 3D information while treating a single node, an amino acid as a node, so that the computation complexity is not increasing while considering this all atom level in 3D information. So the assumption we use here is that all bond lengths and bond angles in each amino acid are fully rigid. So the only remaining degree of freedom is the side chain torsion angles. So we further encode these side chain torsion angles into the 3D geometric representation of the pronet, so we can reach the completeness at all atom level. So to summary of our methods, for the amino acid level, we use the complete 3D GN with an adaptation on our protein structure. For the backbone level, we further incorporate Euler angles between two rigid backbone triangles. And then finally, for the all atom level, we add the side chain torsion angles for each node in the geometric representation, so we can reach completeness at all atom level. So for all 3 levels, the computation complexity is still O and K, that will review each amino acid as one node, and while adding more internal structure information, but not increasing the computation complexity. So here's a general framework for our pronet. So here we have a geometric representation for a graph, and we can just fit them into some basic function to get a geometric representation, and then fit all the information into a convolutional graph convolution networks, and use this as in the interaction block for each graph. And then we get the node representation, node embedding for each node here. And we use some kind of classifier or MLP to aggregate all node features and into a single representation vector. Then we can predict some kind of property of the molecules. Then, yeah, so then we get the final output of this model. So here for the tasks, we evaluate our ProNet on various protein tasks, including protein fold and interaction classification. So we can treat these two tasks like some kind of protein function protein function prediction, that the input is only one protein structure and the output should be related to the function of this protein. So here the matrix is the accuracy on the classification tasks, and we can see that our ProNet works pretty well on these two tasks. And also the protein backbone methods works the best among all three levels. So we also evaluate our ProNet on two interaction tasks, so-called the protein ligand binding affinity prediction and protein-protein interaction prediction, that we need to take two structure as input, and we want to predict the interaction, how this two structure interacts, like the value between these two structures. And we can also say that for the interaction tasks, our model also works well, that outperforms all previous baselines. And also our ProNet all atom level works the best among all three levels. Wait, I will skip this for time consideration. So to sum up, that our ProNet, we proposed hierarchical and complete representation for protein representation learning. And also we evaluate our network on different downstream tasks, and which the results show that different downstream tasks may require methods at different levels. Like the backbone level works better on function prediction tasks, and all atom level works better on interaction prediction tasks. And also on the efficiency analysis of our method, that our computation complexity at all levels is still O small nk, and which is more efficient than baseline methods. So also I want to note that the mainly takeaway for our talk for our method is that when considering designing structure representation, we need to consider the completeness of the structure. Also, different downstream tasks may require methods at different levels. Right. So the code for our method can be found in this library for graph deep learning research. And also, right. So that's all for my talk today. Thank you so much.
Thank you, Haran. This is really interesting. Let's again wait and see if there are any questions pop up on the chat. So I have a really quick question. So like you're proposing like 3 different levels to represent this graph, and then have you ever done like an ablation study to see like which level performs, contribute the most to the task?
Yeah, we have a specific like ablation study in our paper, and actually we found that different downstream tasks may require different granularities, like different resolution for the structure. Like the backbone method may works better for function prediction tasks, that generally if we have the backbone of the structure, like we have a general shape of the structure, that will be enough. But for interaction, that would be for interaction prediction, that we need to look more closer on the side chain interactions, so that we need all atom level methods. Yeah, so I think that would be a very interesting, like also a very interesting observation for that may benefits all the fields for designing all future representation learning for proteins models. Yeah.
Yeah. Yeah, thank you. And also according to the efficiency part, so the algorithm you propose achieves a big O of n times with k. So I'm just curious, like, what about the other like baseline models? Are they really done this? How are the efficiency would be like for them?
Yeah, sure. So when comparing like the efficiency, generally, if we consider each amino acid as a node in the model, that would be of O small n k. But if we want to make use of all like coordinates, like we want to treat each atom in the protein as a node, like that, the computation complexity will be increased by maybe 4 to 5 times, and the complexity will be O big n k. Yeah, since each amino acid may contain 4 to 10 atoms, and it has its own inner structure at each amino acid.
I see. Yeah, it's a big improvement, I think. Right. Yeah, we're I think we can finish here. Thank you so much, Haren, for sharing this interesting talk. Thank you. So let's now welcome the last speaker, who is Lan Huang he's currently a PhD student at the University of Tokyo. Yeah, so you can start when you're ready. Thank you. Yeah, we can see the screen.
Okay, can you hear me?
Yes.
Yeah, cool. So, hi everyone, this is Lang from the University of Tokyo, and today I'm going to present our work, Self-Adaptive Training, Bridging Supervised and Self-Supervised Learning. This is a joint work with Chao from Peking University and Hongyang from the University of Waterloo. So before I dive into our work, let me just give a bit background of this work. And I guess all of you may already know the prevailing learning paradigm in current deep learning era, that we start from a large pre-training data, like in computer vision. ImageNet may be one of the most commonly used pre-training data set. So with this kind of large data sets, we first pre-train a deep network based on this kind of large data set. And then we just transfer the pre-trained network, transfer the model weights to the other data set with smaller scale, like the CUB burst in this case. And this is the prevailing paradigm in deep learning. The problem for this matter is that in many real cases that we may encounter some noisy data set, like the labeling is very noisy due to the nature of manual annotation. Like in the figures below, the original label is wrong, and it's caused by many aspects of the annotation nature. So it's inevitable. And some early study also show that the portion of the noise in the data could be very large, like in the ImageNet test set. They estimate that there might be roughly like 5.8% of the test label is wrong. So this is not negligible portion of noise in the data set. And with this in mind, a natural question is that what happens if we train our models on data set with such kind of noise? Regarding this question, we perform a systematic study to show the training dynamic of the deep model on the corrupted data set. we construct a corrupted data set based on a CIFAR-10 data set. And given the clean CIFAR-10 training and test set, will randomly corrupt the training set and the test set by 4 kinds of corruptions. We corrupt 40% of the data by the corruption like label noise, like we corrupt the label, we randomly flip the label, or we replace the image by Gaussian noise, or randomly shuffle the pixels of the image using a fixed pattern or determined pattern across all the data set. So here we got 4 subsets of the data: the clean training set, the clean test set, and noisy training set, and the noisy test set. So with these 4 subsets of data, we train the deep network based on the standard training algorithm, which is the empirical risk minimization with cross entropy loss. Here, the F theta here is the deep network we care about, and the X is the image, and Y is the label associated with the image, and log L is the cross entropy loss. So we just minimize the empirical cross entropy loss over the data set to train the model. So let's see what happened when we train on this or train on the noisy training set and test the performance on all 3 other data sets. So here we actually have several observations on the training dynamic of deep models. The first observation is that on 4 noisy training sets that constructed by different corruption setting, we can see the EIM achieve nearly perfect training accuracy, which is indicated by the red curve. The red curve eventually reached the 100% at the end of training. But on the other hand, we can see the generalization behavior of these 4 subfigure is very different. Like we can see the gaps between the noisy and the noisy training and test set, which is the red and the blue curves here. The gap is very large in the first figure, and it becomes smaller at the other figure. So this is the 2 observations of the deep model that we can see the EIM easily overfits noise. And another 2 interesting observation we have here is that actually we find the overfitting to the noise occurs only after certain epochs. Like in all these 4 subfigures, we can see the red curve and the blue curve is actually very close to each other at the first few training epoch. Like before 15 epochs, we can see the red curve and the blue curve is very close to each other. So the overfitting does not happen there. And the second observation is that we find that the model prediction can actually magnify the useful information in the data. So let's see the curve of the clean validation set, or the curve of the clean training set, which is the sine curve and the yellow curve here. So we can see on all 4 subfigure, the accuracy on the clean subset, on the clean training set or the clean validation set, they all surpass the percentage of the clean data in the noisy training set. Like in the we corrupt 40% of the data, so the percentage of the correct data in the training set is about 60%. But in all these 4 subfigures, we have a peak clean training accuracy or the peak clean validation training accuracy above 80%. So we have 20% improvement if we train on this kind of noise label. Even 40% of the data is corrupted. So we can see the model prediction actually can magnify the useful information in the data. So this is the case of the data corruption. And another interesting analysis we conducted is that what if we just replace 100% of the training data, the training target with noise, like we replace the labels in the CIVA-10, the one hot label in the CIVA-10 with 100% Gaussian noise, the random sample, or we just replace the labels of the CIVA-10 training set with the output of a randomly initialized and then fixed model. And in such cases, we can see it is actually identical to the cases of self-supervised learning, where we do not have any label associated with the image. We just have the image themselves, and we train the model without any solution. Okay, so in this case, we simply change the training loss from the cross-entropy loss to the mean square error between the network output and the noise. And here we used another evaluation to monitor the training dynamic by we initialize a linear classifier atop the frozen deep network, and we train only this classifier with the label to see how we how the performance of the representation. Okay, so we have several interesting observations on this setting. And the first is that fitting both kinds of the noise achieve better performance than a random initialized model, which is the indicated by the horizontal line. So this again suggested that the model prediction can actually magnify the information underlying the data, even without the labels. So this is the first observation. And the second observation is that we can see fitting the Gaussian noise, which is the green curve, is better. And this is potentially due to its consistency compared with using the output of a fixed model as training target. So with this analysis in mind, we had some inspiration for our methodology that we try to incorporate the model prediction to augment the training process, and we want to do it in a dynamic and consistent manner. And we also, with the analysis we have, we can see that behavior of supervised and self-supervised learning is quite the same. So we can unify the training of these two learning paradigms into a single training framework. So, okay, so here we propose a meta algorithm called self-adaptive training, and it can be adapted to both supervised and self-supervised learning with 3 modules. And here we have 3 modules to be instantiated according to different learning paradigm. The first is how we initialize the training target. Like in the supervised learning, we have the label, so we can initialize the target with label. But in self-supervised learning, we don't have any label, so we just leave this part as a random noise. And the second part of the second module is the normalization function used for different learning paradigm. And the last one is the loss function. Okay, so based on these three modules, the algorithm for self-adaptive training is actually very simple. So with a data set X and TI, so in each training iteration, we simply just take the prediction of the model on the image XI, which is denoted by the PI here, which is the prediction. We just incorporate the prediction PI into the training target TI with a simple exponential moving average by consistently and smoothly interpolate the prediction with the training target, and the other part of the training is remain unchanged during the training process. So this is the meta algorithm for self-adaptive training. Okay, so next step is that we show how we adapt our self-adaptive training for different learning paradigm. And for the supervised learning paradigm, it's actually very simple and it's a drop-in replacement with the empirical risk minimization. Again, here we just change the three components mentioned above, that we initialize the training target by the original training label, which may be noisy. And the second part is the normalization function. So here the normalization function is in the fifth line. It's the softmax function that normalizes the model prediction into a probability distribution. And the third part is the training loss function. Here we use the cross entropy loss. So with these three modules specific to the supervised learning, we are able to adapt our algorithm for supervised learning. And the two key components of our algorithm for supervised learning here is first is on the within the yellow rectangle that we correct the erroneous labeling by exponential moving average, and the second part is within the green rectangle that we use a sample reweighting scheme based on the training target that we accumulated during the training. So the intuition on these two scheme here is that with the ERM scheme, we are able to accumulate the model prediction after the models at the point that models start to overfit data. So we like warm start the training at the first two ES epochs where the model are fitting the correct labels, and then after ES epochs we start to correct the potentially erroneous labeling by the model prediction here. So this is the intuition for the first part. And the intuition for the second part, the sample reweighting part, is that given the training target TI, we can actually simply use the maximal element of TI as the labeling confidence of this sample. So with this confidence, we can just reweight the different sample in current batch to like downweight the sample with uncertain labeling and upweight the sample with certain labeling. So we just select the different sample with different labeling confidence. Okay, so with this algorithm, we can see some interesting analysis here. So on the four kinds of random noises here, compare with the baseline empirical risk minimization, we can see our algorithm actually mitigates the overfitting issues. We can see the record of our method do not converge to the perfect training accuracy. The second observation is that the generalization error is also reduced compared with the baseline. Like we can see the gap between the red curve and the blue curve is significantly narrowed in our method. And the third observation is that our algorithm can also boost the performance on the clean data. See the cyan curves here that we have a higher validation accuracy compared with the baseline on all 4 kinds of random noise. So this is the first analysis that we varying the different kind of noise and to see how the algorithm performs on such settings. And the second part of this analysis is that we try to varying the noise scheme. Like we have different levels of the noise. We inject like 0% of the noise into the data, or we inject like 90% of the noise into the training data. We can see on all noise levels, our algorithm can actually reduce the generalization error compared with the baseline, which is represented by the dotted line here, and we have much lower generalization error, and we also have higher or lower validation error clean on the clean validation set compared with the baseline. So this suggests that we not only underfit the training data, we actually this method can calibrate the training. We improve generalization performance and improve clean classification performance. So this is the analysis on some random noise. And we also have another analysis that we try to vary the model capacity. Like we change the width of the ResNet 18 model by varying its width from 1 to 16.4. And we can see our method actually outperformed the baseline when the model with sufficient capacity. And it shows a vanish double descent phenomenon where we can see our method, the test error of our method decreases monotonously with respect to the model capacity. While for the baseline, we observe an intriguing double descent phenomenon that the test error first decrease with respect to the model capacity and then increase and finally present another decrease in this process. And our method also only exhibit the single descent phenomenon here. Okay, so other than the random noise, we also have another analysis on the adversarial noise, where adversarial noise is another kind of noise that is human imperceptible, and it is a model dependent noise. That, like in this figure, we have a figure of panda, and we add such kind of small noise to the panda, and the model may fail to recognize it as a panda. So our experience shows that the state-of-the-art adversarial training algorithm actually overfits the adversarial noise. And with our training algorithm, we can mitigate this overfitting and finally improve the performance on the adversarial data. Okay, so I'm going to present a few application of this method. The first one is on the noisy classification, where the training set is consists of several levels of the noise, and on all training on all noise level and under all data set, our method actually perform better than the baseline on most of the entry except one entry, and advances the state of the art by up to 9% in absolute. So yeah, this is the first application here, and we have some ablation story to show how we recover the label and how we accurately reweight the sample according to the label quality. So in the first figure, we have the left figure, we have the confusion matrix of the recovered label with respect to the clean label. We can see the diagonal blocks are with much higher weights than the off-diagonal blocks, and the average result of the label recovery we have is we can correct the label of the 94% of the sample when our training data contain 40% of the noise. And the right figure here shows that our method can actually probably outweigh the benign sample, where the diagonal block again is the sample with the correct label in the noisy training set. We can see the weights for this block is much higher than the weights in other off-diagonal blocks. Okay, so the second application of our algorithm is a task called selective classification, where the model is allowed to output an option called don't know that we refuse to make prediction on these highly uncertain samples. And under such kind of setting, our algorithm also have higher classification accuracy and a different prediction coverage compared with previous method. Okay, so this is some application of our algorithm with supervised learning. And for the self-supervised learning part, we again can adapt our algorithm with 3 components, make some minor modification. The first part is how we initialize the training target. Here because we don't have any label, we just randomly initialize the training target TI by some random Gaussian noise, as in the second line. And for the normalized function, here we choose L2 normalized here, as shown in the eighth line. And the loss function here is the mean square error between the prediction and the training target again. So here the major component is within the yellow rectangle, where we try to incorporate the model prediction with the exponential moving average. So with this kind of small modification, we can adapt our algorithm to self-supervised learning. And the overview of our algorithm for self-supervised learning is shown in this diagram, that for each training image, we have some data annotation, and we fit this image into a backbone to extract the feature. And projected into a lower dimension. And we can, here we have two branches. The upper branch is the branch with gradient updates, and the lower branch is the so-called momentum encoder that do not have any gradient update. It's just a exponential moving edge copy of the upper branch here. And the training loss of this of our method is the MSU loss between the prediction PI and the training target TI that updated by the training target with EMA here. So the overall training diagram for our method is as in this diagram. Okay, so with this method, we can see that again with the same experiment as the previous figure, we can see fitting the accumulated representation, which is exactly what we done in our method, consistently and substantially improve the representation of the models. And you can see from the blue curves here. And next I will dive into some real experiment to show the improvement of our method. And the first one is to improve training efficiency compared with prior self-supervised learning method. We can say like half of the training cost compared with the most closely related work bio here. And regarding the components, the complexity of the model, we have several ablation studies to show that our method can work using only single augmentation view. Where augmentation, what we mean augmentation here is that like in this figure, we have a single augmentation view, so we only have one image after the augmentation. If we adopt a two augmentation view training system, we have two augmented view after the data augmentation step. So here we only adopt a single augmentation view for training, and we can see our method can work in the lab table. We can see our method can work without multiple view in the training. However, the baseline method, their performance is nearly half when only using a single view. And in the right figure, and without two other components like the predictor or the momentum encoder, which is some necessary component for the baseline, this baseline failed to work with these two components. On the other hand, our method can work even without none of these components. So we can see our method have more robustness to the component design compared with the baseline. Okay, so finally, we have some experiment on the larger data set where we train a ResNet 15 model on the imaging data set and evaluate the performance of the models on using a linear classifier atop the pre-trained model. And we can see that the single view self-adaptive training, which is also already comparable with the prior method with two augmentation view. And if we use two augmentation view, we can observe the self-adaptive training outperform other method with even more training epoch than like 4 times more training epochs than our method. So this suggests the efficiency of our and the effectiveness of our algorithm for self-supervised learning. And we also have some transfer learning experiment that we perform like comparably with all other baseline on this object detection benchmark or semantic segmentation benchmark here. Okay, so to sum up this talk here, in this talk, we observe that useful information from the data is implicitly distilled into the model prediction. And this observation occurs broadly even in the presence of the data corruption and the absence of the labels. And regarding this observation, we propose a learning algorithm called self-adaptive training for both supervised and self-supervised learning. And it is a general training algorithm that dynamically incorporate the model prediction into the training process. So, okay, so that's all of my presentation. So thank you. If you have any question, feel free to ask.
Yeah, thank you so much for this interesting talk. Let's wait for a second to see if there are questions coming up. I have a quick question. Please just correct me if I'm wrong. So it feels like to me the self-adaptive training looks like the boosting algorithms, right? So for each epoch, you recalculate the weights of each sample and then kind of adaptive training the
yeah. So in the supervised learning or it kind of boosting algorithm that will reweight different sample based on their training targets. But I mean the reweighting part is actually not necessary for this matter. We have some experiments to show that the most important part is we incorporate the model prediction using the EMA, and the reweighting part can contribute a little bit more than we just use the EMA of the model prediction. But the most important part is the EMA here. So yeah.
Let's see.
Yeah, the question. Yeah.
Thank you so much. Okay, I think actually we're out of time, but thank you again, Ram, for this. So I wish to quickly close this AI seminar today. I want to thank again for all of the speakers who contributed a lot to this event to happen. And also thank you so much for all of the participants who stay here with us for like 5.5 hours or so. Yeah, thank you very much. So I will try to follow up and upload all of the materials for today, just in case you miss anything. Okay, so thank you so much. Have a good day or have a good night. Thank you.